We are glad to see you today. My name is Sergey Karapetyan, and I I work at HEC Faculty of Computer Science. And today we're organizing the webinar of the bootcamp for you on ML competitions. And we'll try to prepare you for future competitions. And I would like to say a couple of words before we actually dive into the wonderful content of the bootcamp. And first of all, once again, I would like to thank you for joining us today, because I know how hard it is to dedicate your weekend to learning instead of walking around, watching series, I know, eat pizza or have great fun. So instead you choose learning, and we are grateful for that. And we hope that in return we will be as productive as possible. Secondly, we have Anastasia joining, and my second point would be thanking every speaker that we have, everybody who helped to prepare the bootcamp, all the wonderful speakers, and particularly Elena Kantonistova, who will join us later as the second speaker for today, and she's the head of the school, and also represent machine learning and data intensive system master programs and program at HEC. What else I would like to say, that what's the point of organizing the whole event? Overall, as you might know, because I actually recognize some names in the list of participants, maybe from summer schools, maybe from IDAO competition. Basically, for last couple of years, we're organizing a IDAO competition with Yandex. It's International Data Analysis Olympiad. And we noticed a thing that some of the participants are not able to properly participate, either submit and good answers or participate at all, because the lack competition experience, contest experience. So that's why we decided to organize this bootcamp as a kind of preparational thing for such contests. So I guess the last thing to say that in terms of contacts, I am on Telegram. So if you have any problems during the bootcamp, I'm available. Also, all the speakers are over there. Feel free to contact us. We'll try to share as much as possible. And schedule is also pinned to send to your emails, and it's on the website and also pinned to the Telegram channel. And the last thing I would like to say, probably it would be nice if you write randomly where you're from, because it would be great to see your geography and see the locations where you're from. So just drop in the chat. Well, basically, I'm right now in Moscow. I guess that Anastasia too. Without further delay, I guess giving up stage to Anastasia Maximovskaya, our first wonderful speaker for today. And Anastasia, the stage is yours, and I'm leaving. Thanks a lot.
Okay, thank you, Sergey. Thank you for this lovely introduction for our bootcamp. So yes, let me introduce myself. My name is Anastasia. I work as a data scientist in Sberbank, where I deal with recommender systems for our e-commerce clients. And as a hobby, I also am a lecturer at Higher School of Economics. And today I'm going to talk to you about different tips and tricks about data preprocessing. So let me share my screen in a bit. Can you see the slides, like the full slides without PowerPoint stuff?
Yes, yes.
Okay, great. Okay, so let's dive right into it. So our plan, wait, give me just a second to turn off different things that the Zoom. Okay, so yes, let's dive right into it. So our plan for today is to talk about different ways of feature encoding, talk about feature generation and feature selection. So except exploratory data analysis, I want to cover as much as possible of everything data related before you start dealing with models during your competition. So okay, something works weird. I hope everything is still fine for you. Okay, so let us start by having a few definitions that I'm sure you're probably familiar with, but anyway, just in case. So for example, we have a task of predicting the profit for a restaurant. And a restaurant is, for now, an object, or in statistics, it's called an observation, or sometimes you can hear a word, a data point. And it is an abstract entity, and computer works with numeric. So we need to find out a way on how to describe that entity with numbers and categories. So feature is the characteristic of an object. And that's why observations can also be called sometimes feature vectors. Let's define for now the following types of features. So the first would be numeric. So in my example with restaurants, it would be the rent for the place, for example, would be a numeric one, or the square footage. Another one would be binary. So for example, is there a kitchen in the restaurant? Binary. If there is, we put 1. If there isn't, we put 0. And stuff like that. Usually these binary features are some kind of question with yes or no answer. So is there a kitchen? Yes and no. Categorical. Categorical is when we have a fixed number of values that this feature can take. For example, the type of cuisine that is served at that restaurant. For example, it could be Italian, Japanese, Chinese, and so on and so forth. Of course, when we are taking the models to production, new categorical values can arise, and that is normal. And we'll talk about how to deal with that in a bit. But for competition, for now, we will assume that they take a fixed number of values. And other types of features, I have called them features with a complex internal structure. And by that, I mean images and text. In my talk today, we are going to be focused more on working with tabular data. So I will talk a little bit about working with text, but about working with text when you are dealing with the tabular data contests. So for natural language processing and computer vision competitions, I suggest you do a bit more research. Moving on to the first topic that I'm going to talk about is feature encoding for categorical features. So the first one is something that most of you have probably heard of, and it is one-hot encoding. So what is one-hot encoding? Here I have my column. Let's say I have a column called pet, and I have 5 values here. I take all of my unique values, for example, cat, dog, turtle, and fish. And I put each unique value as a new column here. And after that, I just fill the matrix that I got with the zeros and ones. So for example, I have cat in my first row, and so I put 1 in the column cat and zeros in everything else. Dog, turtle, fish, and so on. As you can see, zeros and ones everywhere. It's very simple. This is a very simple methodic. And a few things that I would like to point out about that. First of all, if you're using linear models, then beware of multicollinearity. So in order to deal with it, just remove any one of the columns that you have. So for example, remove just the last one. And if we have like a row full of zeros, we will understand that this is not dog, not turtle, not fish. So it will still work. And don't worry about that. Another problem is, for example, imagine that you have a problem of detecting fraud. So you're an insurance company, you have some clients who have some problems with their cars, and they are writing claims to you, and you want to understand which ones of those claims are fraudulent. So in real world, these types of companies, they have a lot of data. So like thousands of rows or even millions sometimes. And of course, the fraud would be just a very small percentage of those things. For example, 0.5% is also a very realistic number. And in claims, there would be written what kind of car the person is driving. So you would have a lot of different cars for a lot of different people. So for example, even in one country, we would have a huge variation of those cars, but technically it would still be a categorical feature. So if you apply one-hot encoding, you would get like a huge sparse matrix that would be very difficult to train models on. And it would be very difficult to derive some kind of conclusions from it. So be very careful of that. And for this type of problem, we'll have some other ways to encode features, which we'll talk about also in a bit. Let me check the chat. I see that there are a lot of messages. Oh, okay, great. No questions so far. We think that I'll answer the questions later at the end of my lecture, so you can still write them. I'll just check them out a bit later. So this is an example of how the formula for linear regression would look like with one-hot encoding, because for linear regression, this is one of the few steps that you need to take in order to get a better result. So basically, it's just this is an indicator that your, for example, column pet is equal to turtle, and this is column pet is equal to fish, and so on. So just this is how a binary column is noted in the formula. So just an example. Moving on is ordinal encoding, and here is where I want you to pay close attention. So as you can see this picture here, I'm sure you have seen it a ton of times, and I'm sure you have used the label encoder for those. So let's talk a bit about that. So if you remember my example with restaurants, when you have a few restaurants and you want to predict their profit, and you have a column that says their types of cuisine. So this would be a categorical column. So your first thought would be to just, so we need to create numbers from the column with words. So the first thought would be, okay, let's just say that Italian cuisine would be 0, Chinese cuisine would be 1, Japanese cuisine would be 2, Russian cuisine would be 3, and stuff like that. But when you're doing that, some models may think that if Italian cuisine is 0 and Japanese cuisine is 2, then Japanese is better than Italian. And we do not have that kind of dependency in our data. So that is why be very careful of when you're using these types of encoding. And a situation where this would be appropriate would be, for example, with higher education. So bachelor's degree is higher than high school, master's degree is higher than bachelor's, PhD is higher than master's, and so on. So here would be logical to put like high school is 1, bachelor's is 2, master's is 3, PhD is 4, and so on and so forth. That would be a pretty logical solution. Another thing that I would like to mention here is about scikit-learn library. So there are 2 ways to do this thing in scikit-learn, if I remember correctly. The first would be a label encoder, and the second would be ordinal encoder. So for some reason, I always see my students, they use a label encoder, but if you try to apply it to multiple columns at once, it does not work that way. It only takes 1 column as an input. And that is because it is a subtle hint from scikit-learn developers to you that label encoder was meant to be used on your target variable. So if you have a task of multi-class classification, then you would need to encode it some sort of way like this one, and the label encoder should be used there. And ordinal encoding, it allows you to transform multiple columns at once. So that is also like a subtle hint on where to use these modules. Okay, that is everything that I wanted to say here. So yeah, my main thought here is that we need to, the good place to use it would be where we have some kind of dependency in the data, hierarchy in the data would be even a more accurate way to say this. Okay, moving on. Target encoding, or especially in the example of this picture, sometimes it is called mean encoding. So how does this look like? So for example, let's say we have a categorical feature, let's say job. So we have a job, doctor, teacher, engineer, waiter, and driver. And we have, let's say, a task of binary classification, target, and we have 0s and 1s here. So let's take the first job, which is a doctor. We have 4 rows of those. 4 rows, and for 2 values, the target is 1, and for 2 values, the target is 0. So what do we do here? We find a percentage of 1s divided by the number of rows that have a job equal to doctor. So the number of 1s is 1 and 2, and the number of rows with doctor is 4. So we take 2 divided by 4. This is 1 divided by 2. This is 0.5. Here it is. So we put 0.5 in our job mean variable. The second example would be with teacher. So as you can see, we have 2 rows, and both of those rows have a target variable equal to 1. So we take 2 1s. So here we divide by the number of rows, which is also 2. So 2 divided by 2 is 1. So we put 1 in our job mean column. The third would be engineer, and I'm sure you already understand the gist of what I'm saying. We have 2 rows, one of them is 1, so we divide 1 by 2, and we have 0.5 again. And waiter and driver, we only have 1 row per them, so that is just a duplicating of target. We just duplicate the target variable. So we have 1 here, we put 1 here, because 1 divided by 1 is 1. We have 0 here, so 0 divided by 1 would be 0, so we put 0 here. So this way to encode the data, the categorical data, is called target encoding, or you can also find it by mean encoding. I'm not sure if it exists in popular libraries like scikit-learn, but I'm sure you can Google the functions or write the one yourself. It's pretty easy, as you can see. What are the possible problems here? Well, the first problem is pretty obvious. We are encoding our information about our target variable into our independent variables here. So we basically create a small data leak for ourselves. which will result in better metrics, better results of your metrics, but can also lead to overfitting, and you should be very careful when using that method. So it is very popular on competitions, but be very careful with using it. So just make triple checks about overfitting. So that is one way. Another way is to, if we, for example, here I use target encoding, but you can also do not target encoding, but something else. For example, we have another independent variable here, like is there a kitchen? So ones and zeros, or stuff like that. Or is married, also ones and zeros, not a target variable. So just encode by that. So we can encode from one variable to another, and it can also work. It is also actually, we'll talk about that. It is also a way for feature generation and can sometimes be useful, especially in these types of competitions. What else? Here we're using min function. So we have like 2 ones here divided by 4 rows here, get 0.4, everything's great. You can also use other types of functions, and there are examples of how to use those. And again, your imagination is your limit. So you can also change the types of functions that you use here to aggregate this type of the data. And it also sometimes works. And I have seen people use this strategy in Kaggle competitions, and that it has yielded them good results. So that's about target encoding. I think I have said everything. So to sum up, what do we have here? This is how it's calculated. We can encode by target, but then we risk being overfitted. And we can also encode by some other variable in our feature space. And we can also use something else instead of min. So those are my 3 main theses for today. Okay, moving on. Another great way to encode features is feature hashing, or sometimes known as hashing creek. So what is it? Well, feature hashing basically maps each category in a categorical feature to an integer within a predetermined range, by you. This output range would be smaller than the input range, so multiple categories may be mapped to the same integer. And feature hashing is very similar actually to one-hot encoding. You will see in a minute why, but with the control over the output dimensions. So let's take a look at the example of how it is calculated so that we can understand it better. But before we dive into that example, let me give you a few reminders of the terms array and linked list. So array is, well, we all know what array is. So this is a collection of some values, and the values have indices, and the indices, they have a fixed number of values that can be in an array. So that is like this. And we can use indices to access the values. So by index 3, I can access the value 4. That is what an array is. We also have another term that is called linked list. So in linked list, we store the path to the next value in the previous value. So that way we can grow dynamically and can have and do not have like a fixed size. But since we have to sequentially get from one point to another to get to some value, that would be very time consuming and can yield bad performance. Okay, so now that we have remembered the basics of array and linked lists, let's move on to feature hashing and see how they can help us there. So we have our feature, let's say categorical feature, but this can also be used on text. So let's say the value for a categorical feature is blue. Then we use some kind of hash functions. In Python, there is a library called hashleap. You can check it out. And there are a lot of different hash functions there. And I think the most popular among other libraries would be Murmur3, but I'm not sure. I think it is. Well, a couple of years ago it was. Now I'm not so sure. So these types of hash function, it gives us a very big number. So we want to encode this number somehow, and we would do it by dividing it by some number and taking the remainder of that division. So, a question to the audience. What is the Python symbol for taking the remainder? Do you remember? Okay, so here in the first example, we divide by 8 and take the remainder of the division. In the second example, divide by 5, take the remainder of the division, and so on and so forth. Here you yourself choose what number are you going to divide by, and that would be the range for your features. So let's say that for blue, we have, if we divide by 8, we would have the remainder of 7. If we divide by 50, we would have the remainder of 1. And if we have the division by 100, we would have the remainder of 51. For some reason, I can't see shit. Oh yeah, great. Everyone remembers. Very good. Let me move back a couple of slides. Okay, so for example, we have encoded a few values. So let's say we put the word red in our hash function and divided it, for example, let's say by 8. And the remainder was equal to 3. So we put red. So we have a small table now. We have a table of 8 rows because we chose to divide the result of our hash function by 8. So we have and take the remainder of division by 8. So we have 8 rows here. And let's say that the remainder was equal to 3. So we put red in the row 3. And let's say for the blue and green, the remainder of division by 8 was 7 for both of these words. So this is called a collision. It's not very good. And usually people take bigger numbers so they won't get as much collisions. But we have a way to deal with it now that we know what a linked list is. So basically we create a linked list here and use it. Let's look at an example. Let's look at a more detailed example with a table that I think would be more intuitively easier to understand. So here we have the categorical feature color. We have 3 values, red, blue, green. We have the results of some kind of hash function, and those are numbers. We divide by 8 and take the remainder of the division. And here it is 3, 7, and 7. So we have 7 columns, 8 columns actually, because we choose to divide by 8. We put 1 here in our feature 3, in our column 3, because the remainder was 3. And we put 1 in the last column, which would be the column number 8. Or if you are counting down from 0, it would be number 7. And we put 1s here. So this is a collision, and this would how a linked list would be looking if we just created this feature hash in our regular pandas and NumPy and other Python libraries. So this is how it would look like. So as you can see here, it is very similar to one-hot encoding. We still have a sparse matrix of a lot of 1s and 0s. But now we actually have the control of how much features would we have in the result. So that is a bonus. And you can implement it using category encoders library. And you can also use other hash functions from HashLib, as I have previously stated. And pro tip, actually in this category encoders library, I think you have probably heard of it. And if not, I definitely recommend you to check it out, because there are a lot of ways to encode other categorical features that did not fit into my lecture. My goal today was to talk about most popular ways that I have seen win the Kaggle competitions. But you can also look at some other less popular ways and category encoders, and maybe they would help you a lot. Okay, moving on. Weight of evidence. So what is weight of evidence and how do we use that? So the goal of a weight of evidence is to sufficiently identify the best recording to weight of evidence values for a list of categorical predictors and to assign to each category a unique weight of evidence value. So that sounds a bit confusing. Wait a couple of minutes and I'll move on to another example. So weight of evidence could be used for combining variable groups levels, and this process is called coarse classing. We'll talk about this process a bit later. It is actually another crucial step in preparing you for our data analysis Olympiad. And yeah, we combine categories with similar weight of evidence and then replace the categories with continuous weight of evidence values. So basically this weight of evidence thing was created in credit scoring or bank scoring, I don't remember, task, or something with scoring and finance, that's that kind of stuff. And the example that is usually taught in different courses and tutorials is how we take good clients and bad clients. So here, one of the ways to calculate the weight of evidence is to divide the percentage of non-events to the percentage of events. So let us take a look at an example. So for example, we have some kind of feature. So feature that can take 3 values, A, B, or C. And we have our outcome. Outcome, let's say we have a task of binary classification, just zeros and ones. So ones and zeros. So how do we calculate weight of evidence? Well, let's first of all calculate the non-events. So for group A, we have 4 rows in common, in total, and we have 3 events. Events would be zeros, non-events would be ones, and non-events would be zeros, I'm sorry. So yes, events would be ones. So we have 3 ones here. So we have 3 events here. And we have 1 0 here, which would be 1 non-event here. The next category here is B. So for B, we have 2 ones and 1 0. So 2 events and 1 non-event. Put it on the table here and here. And the last group would be C. Group C would be just the ones. So only events, so 0 non-events and 2 events. Now let's calculate the percentage. So be careful here. This is a tricky part. So we have 2 zeros, 2 non-events in our whole data set. So yeah, this is like this example, this would be our whole data set. So in group A, we have this 1 non-event. So group A would have 50% of non-events. Then group B would have another 50% of non-events because we have the second 0 here. And group C would have 0% of non-events because we don't have zeros here at all. We only have ones, which are events. Then the percent of events. The percent of events here would be, I think we have 1, 2, 3, 4, 5, 6, 7 ones here, and we have 3 of those in our group A. So we take 3 divided by 7, and this would be 0.42 and something. So let's put 42% here. Same for the B category. We have 2 divided by 7, which would be approximately 29. And for C, again, we have 2 events. So we divide 2 by 7, and we have another 29. And here we calculate the weight of evidence by using the formula. So we divide our non-events by events and take the natural logarithm of it. And here we have some kind of values. So now we take those weight of evidence events, or you can just divide the percentage. So you can just divide 0.5 by 0.42. I have seen people do that as well, without like adding 0.5 here, dividing by 2, without like this kind of normalizing. I have seen people do that as well. Well, as always, a lot of different variations for the most popular approaches. So what else? Now we have our weight of evidence for our 3 categories. So we have 0.4 for A, we have 0.70 for B, and we have minus 0.35 for C. So let's transform our table. And after the transformation, our table would look like this. We put 0.4 as weight of evidence for each value in the group A. We put 0.74 for each value in group B after calculating the weight of evidence. And for group C, we put minus 0.35. So that is how it works. Now we have this weight of evidence, and some papers suggest that we take the categories that have very similar weight of evidence, and we treat them as one because their values are very similar, and the information that they are given to the model would be also pretty similar. So that is another thing that I want to show you here, that if the weight of evidence is pretty similar, you can treat this category, those categories as one. Okay, and another thing that is usually taught while speaking of weight of evidence is information value. So information value would be calculated like this. So we take the percentage of non-events minus the percentage of events, and we multiply it by weight of evidence for each possible group. And then we calculate the sum. So this is how to read this formula. Again, we just take the percentage of non-events minus of event, percentage of events, and multiply it by weight of evidence for that category, and do that for every category, and take the sum of these numbers. And so that would be our information value. So let's do it. Let's do it for our example. So here we have our calculated weight of evidence that looks like this. And let's calculate information value. So it would be percentage of non-events, which is 0.5 here, minus percentage of events, which is 0.42 here. Well, here we have written it in the percent, but I think you realized that I just divided them by 100. And so I do that to get the percentage. And so I do that and multiply it by weight of evidence, which is 0.4 for the first group A. And I get 0.032. And then for the B part, we have 0.5 minus 0.29 multiplied by, I think there's a typo here. It should be saying 0.74, of course. I think it's a typo here. Don't mind. It should be 0.74 here. And it would be equal to 0.048. What else? We have our last category C. So 0 minus 0.22. So beware, we have a minus sign here, negative value. And we multiplied by minus 0.35. So we have a negative 0.29 multiplied by negative 0.35. So we have a positive value. So it would be 0.105. And then we take the sum of these all values. So we just sum these three numbers, and the sum of these three numbers would be 0.221. Here is how it looks. And what does this number mean to us? So how can we interpret that? Well, for that, we have rules for information value. Yet again, as always in data science, these rules, you can tweak them a bit if you want. So this is just something to keep in mind when you're using the information value. You don't have to, if for example, you have like 1 point or I don't know, 03.001, then you understand that it would be like here. So it's okay sometimes to round things up for a bit, and don't treat this as rules that you should always be following no matter what you have in your data. So as always, yeah, it's like maths and just general sense. But let's talk about the rules. And the rules for information values are as follows. So if the information value is less than 0.02, then we say that this variable is not useful for prediction at all. So this variable for which we have calculated the weight of evidence is not useful for prediction. If it has values from 0.2 to 0.02 to 0.1, that is a weak predictive power. And from 0.1 to 0.3, that is medium predictive power. From 0.3 to 0.5 is strong predictive power. And more than 0.5 is suspiciously high predictive power. What does suspiciously high predictive power means? Well, in this type of like Kaggle and other machine learning competitions, sometimes the organizers by mistake or on purpose, they put a bit of data leak in the data. And if you don't find out that you have a data leak, then you can easily overfit and get like a very high score on the public leaderboard that you can see before a competition ends, but then go then go down after the private leaderboard is published and your results are calculated on the whole data that the organizers have. So it is useful to detect the data leak, or sometimes you can create a data leak for yourself without even knowing it. If the data is very domain specific and you are not very familiar with the domain, another very realistic scenario. So be careful with super valuable features, and you can test it out just or use some math test, or you can just use the general sense to understand whether this variable should be this strong for your prediction, and isn't it leaking the data in some way. So here we have our information value equal to 0.221, which is here is called medium predictive power, and we say that is great. I think if it's not less than 0.02, then you can use it still. Let me check the chat for a bit before we finish with weight of evidence. Okay. I did not see any questions straightforward. I see that there is a discussion, and I will try to look at it as much as possible after I finish with the slides. But for now, let's move on. And to sum up, what our weight of evidence transformations does for us. So it helps us to handle missing values. First of all, because it calculates the same number for every category. it handles categorical variables, so there is no need for dummy variables, which is another plus. So we don't have more features and the problems that come with them. And the transformation is based on logarithmic value of distributions, which is aligned with logistic regression output function. So if you want to, so it can also be used there. Moving on, let's talk about feature encoding for numeric features. Well, I don't have a lot here, just an example with binning numeric features. So for example, you are trying to run a linear regression and let's say you're predicting the cost of the rent for the place in dependence on how much time does it take to get to the place from, I don't know, subway station. And let's say it looks something like this. So if it is right next to the subway station, it is expensive. It is a bit of walk. If it is like 10 or 15-minute walk, then the price goes down a bit, and then it rises and then goes in some kind of plateau. So this type of dependency would not be caught by the simple linear regression because it requires the linear dependency between the feature and the target variable. So the way to deal with it is to bin this numeric feature. What is binning? We just take the certain ranges. I can't see my cursor for some reason. This Zoom sometimes works weird. Give me just a second. Okay, well, then I can't draw for some reason, but I hope you can still understand what I'm trying to say to you. So our logic here would be to detect a few places where our price is going like up or down or up again, or it just stays in a plateau. So once we do that, we have some kind of ranges. So if our place is like 0 to 5 minutes of walk, then the price is rising. So that is a linear relationship that linear regression would catch. And we put it here as a binary feature. So whether this apartment is from 1 to like 5 minutes walk away from the station. So if it is, we put 1. If it isn't, we put 0. And so on. We find a few of those regions and we create a few of the binary features, and that is called binning numeric features. Give me just a second to deal with Zoom issues here. For some reason, I cannot, when I'm drawing in a presentation, I cannot just, I cannot see the cursor, so my drawings are not so great usually, but I hope you understand the gist. So we can just take the some kind of numeric features, divided in some types of ranges built upon some logic that is required by the model, and just bin those ranges. So 1 if the object is in this range, and 0 otherwise. So here is how we do binning. Moving on. Yes, this is a very simple example of binning. So let's say we have a variable called age. And if we sort it, we have something like this. So from 10 to 75. And let's create 3 attributes. Again, the way that you define those ranges is should be derived from the model requirements for the data and from your exploratory data analysis. So again, this is not something that is done just by guess. You do need to have some type of reasoning for it. But here, let's say that we have like one group that would be from 10 to 19. The second group would be from 30 to 42. And the third group would be from 70 to 75. And we would have 3 columns. Here, like, is the person like in young category, mature, or old? So 1s and 0s in those 3 categories. It's a bit harsh, those names, mature, for just 30-year-olds. Well, I hope nobody is offended. We did not mean that. And moving on, I think the example with binning numerical features is pretty simple, and there are a lot of, again, ways to modify this idea, but the idea is pretty similar across a lot of libraries. So if you understand how this works, it shouldn't be a problem for you to code it and to modify it even a bit for your competition. So let's talk about text features. Before I start talking about text features, I want to specifically point out that this is not to prepare you for natural language contest competition. And if you are going to take a part in something like that, you need to do some extra research. So what I am going to show to you is something that can be used if you have a tabular contest and tabular data for your contest. And you want to encode it in some kind of way, but not to spend too much time on working with texts. So this is what I'm going to talk to you about. For natural language competitions, again, there are a lot of state-of-the-art methods, and most of them often change. So you can do your own research, or if you want, I can recommend you some books in our Telegram chat. So a few words about text preprocessing before we dive into the ways to encode it. The first thing that you may want to do is to remove the stop words. Stop words are just the noise that isn't interesting for you. For example, articles like a table, like a gives us nothing. Like good table gives us something, some value, and some. This is a description that can be interesting for us. But a table, the table, his table, her table, not very interesting. So those can be stop words, and we can remove them. Lemmatization is to take the lemma of a word. Don't have any good examples in English. I think in English it would be like from sits get sit. So she sits, or she is sitting, and we take the sit. I think it would be something like that. Stemming, get the base of the word, and removing punctuation. Again, this text preprocessing steps are, you do not always have to do them, all of them one by one. No, of course not. For example, sometimes there is a very old example of analyzing tweets from like 2014, where just remove where you leave the punctuation and use just the brackets. Russian people usually use like some type of brackets to depict their mood. So one bracket like this would be like a good mood, a bracket like this would be a bad mood. So those brackets turned out to be great predictors. So you do not always have to do all those steps for text preprocessing. Just know that there are these approaches and use them if you want, if you understand why you do this. So yet again, no strict rules here. Moving on, another thing that I want to show you is n-grams. So what is an n-gram? Again, this is a part of the text, a small part of the text. If, for example, we have n equal to 1, this would be a word. So we split, so the simplest way to get n-grams would be a string dot split. This would create a list of strings separated by the space between them. So n-grams with n equal to 1 would be called unigrams. So for example, here we would have this is a sentence as unigram. If n is equal to 2, then we take our words by 2 in pairs. So this is a sentence. Be very careful that we have this is a and a sentence, not this is and a sentence, but is a is also included. And when n is equal to 2, as I have said, yes, it is called bigrams. Or when n is equal to 3, this is a sentence. This would be trigrams. And a lot of lecturers usually joke about like with n equal to 5, would this be pentagrams and stuff like that. But actually no, just trigrams. I think after that, I'm not sure if something comes. So yes, those are what n-grams are. And let's move on to talk about how we can vectorize the text. So what is vectorize the text? As I have said, we want to work with computers, and our machine learning models want to work with numbers. And here we have text. So we need to find a way to get numbers from the text. So let's say we have a column, and the column has 4 sentences. There are dog, cat eats dog eats food, red cat eats. So this column, 4 sentences, 4 values in the column, just like that. Well, count vectorizer is very simple, naive way to encode that. It is also, I believe, sometimes called a bag of words. So what do we do here is that we take all our unique values. So for this 4 sentences, the unique values would be the red dog, cat eats, dog we already had, eats we already had here, food is new, red cat eats, we already had all those words. So we have 6 unique words, and we put each word as a column. So the red dog, cat eats food. So this is our all of our unique words. And we fill them with zeros and ones. So the red dog, 1 here, 1 in the column, 1 in the red column, 1 in the dog column, and zeros in other 3 columns. Cat eats dog, 0 here, 0 here, cat eats dog. We have these three ones here. So dog gets food. Yet again, I think you already understand the gist of what I'm saying. We have dog, we have eats, we have food, and zeros in other columns, and red cat eats, and so on. Well, this example is with n-gram equal to 1. We can also create this. We can also do the same thing with n equal to 2. So what I'm saying is, if the n was equal to 2, then we would have the following n-grams. So it would be the red dog, cat eats dog, dog eats food, red cat eats. And all of those would be unique, and we would have one in all the one in all the columns. But I think you understand the gist, that it could be done with n more than just 1, as in this picture. And actually, in the Scalone realization of the count vectorizer, we have an argument that is called n-gram range. So you can take both n-grams and bigrams. For example, if you put n-gram range from 1 to 2, or you can use n-gram range from 1 to 3 and take unigrams, bigrams, and trigrams. Or you can just use the trigrams if you write n-gram range equal to 3, 3. So you can use it in a bit of different ways. Again, no strict rules here. You can try different ways and check out the ones that you like the most. But yes, we do have a strong problem here that our matrix would be huge if we have a real data set. So I think, well, there are a lot of words in English language, and even if we take a very simple sentence, a very simple, just, I don't know, description of a product, for example, it still would have a lot of unique words. So you do understand, if you take like unigrams and bigrams and trigrams, how much data would you have, how much features would you have? And that is not always great. And actually, that is why count vectorizer is sometimes used with the feature hashing that we have talked about before. So the feature hashing that can just adjust the data to a certain range that you predefine by the number that you are dividing your hash result, the results of your hash function. So those two can be used together. And if you are just making some kind of notes while I'm talking, then please make a note about that, about count vectorizer and feature hashing. Okay, moving on. Another way to vectorize the text is to use a TF-IDF vectorizer. So TF-IDF vectorizer, how does it work? So let's say we have a column, and in this column, let's say we have description of products. So we have like, I don't know, 100, let's say 100,000 products, and each product would have its own description, which is a bunch of sentences, and a bunch of sentences contain a bunch of words. So for every word, we'll calculate this value. For every word, very careful of that. We calculate. At first, we take like the first word for the first description of the first product. So we take the number of occurrences of this word in the description of the product. We divide it by the number of the words in this description. So just for the first product, first word, how many times the first word occurred in the description, divided by the number of words in the description. And this thing is called term frequency. We're pretty logical. We calculate the number of appearances of the word in the description. Yes, that would be term frequency. The second thing that we want to calculate is inverse document frequency. So what is inverse document frequency? Again, we're doing it only for the first word of the first description for the first product. So we calculate two things. We calculate how much data do we have. So here we have decided that we have like 100,000 products. And the second thing, and this would be our D. And the second thing that we need to calculate would be the number of products that have our first word in the description. So let's say the first word in the description of the first product will be the word this. So we calculate the number. Well, this is actually not very interesting, but let's say great. Okay, great. So the first word would be great in the description of the first product. So we calculate how many descriptions among all the descriptions of our products have the word great in them. So now that we have this number, we divide the number of the total number of products that we have, like 100,000. We divide by the number of the products that have this term, for example, great, in their review. We divide one number by another, and we take the logarithm. Here we don't have the base for the logarithm, but when the base is not written, it is usually 2 or e, which is 2.7. Because in asymptotics, it doesn't really matter which base you take. The values will be very similar. So now for the first word of the first description for the first product, we have two values. We have term frequency and we have inverse document frequency, and we multiply one thing by the other. And that is called TF-IDF. And we calculate it for every word in our documents. Actually, here, yet again, we can use n-grams. So you can use either words, which would be using unigrams, or we can take the pair of words, which would be bigrams, or like words by 3, which would be trigrams and stuff like that. I think you get the gist. So the result would be very simple, similar to count vectorizer. We will still have a lot of features, and we will still have a lot of zeros, but instead of ones, we would have TF-IDF values. And in my experience, it does work a bit better than just the simple bag of words. Especially for such things as machine learning competition, where people work nonstop to try and create the better methods. Of course, count vectorizer, I don't think would be a very appropriate choice, but TF-IDF vectorizer can actually work. Okay, moving on. Let me just check the chat if I have like some immediate questions. How to understand the stop word? That is a good question. Stop word is something that we can consider a noise that does not give us any information. So article, so a table, A does not give us any information at all. So A can be considered a stop word. Or an apple. N also gives us no information, like good apple gives us information. Tasty apple is also an interesting way to describe an apple, but articles and stuff like that are usually considered stop words because they don't give us any information. And as you can see from looking at how TF-IDF vectorizer and count vectorizer work, you can see that those kind of articles, they would take up more space and we would have more features, even bigger sparse matrices and difficulties with calculations after that. So this is the reason why I want to remove some of the stop words. Okay, and what else did I want to tell you? Oh, I want to tell you that, of course, if you're using like some advanced natural language processing competition, then yeah, you can use other ways to create word embeddings using neural networks and stuff like that. But for my lecture, we are not going to discuss that. You can just check out stuff like Word2Vec and just watch tutorials, or yet again, I can recommend you some courses or books if you want to on that topic. Moving on, let's talk a bit. So we have finished our part with talking about different ways to encode the features. So let me remind you, we have talked about encoding categorical features with one-hot encoding. We talked about ordinal encoding. We talked about feature hashing. We talked about weight of evidence. We talked about binning numeric features, and we talked about a few ways to encode the text in tabular data competitions where you don't want to spend a lot of time working with text. So those are the ways that we have discussed. Yet again, I only have an hour today, and there is a ton of different modifications, and they are emerging each day. And you can also like create your own based on what I'm telling you. So there are a lot of other ways to do this. I wanted to highlight the most popular that are very popular among such platforms, but are not usually included in standard machine learning courses. So here they are. And yes, check out Category Encoders library for more ways to encode categorical features. And I do strongly encourage you, while you are preparing for the Data Science Olympiad, to check out the solutions for similar competitions in the previous years, and check out the way they process the data then. I think it would also help you a great deal if you do that. Moving on, feature generation. The second part of my lecture today is to talk about feature generation. Yet again, very important task, which could be very hard to summarize for this lecture, like to give you like specific examples on how you should always generate your features, because in a lot of cases, this is very task specific or domain specific. But my main goal today is just to remind you that that is a very important, crucial step in solving the machine learning competitions on tabular data. In a lot of cases, simple boostings or just very, very simple neural networks, they win, but with a very smart ways to create new features or encode existing ones. So really working with data can be the key to winning a data science Olympiad. So that is why I do remind you that generating features can actually increase your score a lot. So domain specific. So keep in mind, yes, to create domain specific features, task specific features, and general sense. So what I mean here is about domain specific feature. For example, if you know that you are trying to predict the sales of tours to some hot country, then you do realize that one of the features that would obviously help you would be the season of the year. So you need to include that feature, and that is how you include like domain specific. Task specific is like linear regression, wants you to have like some kind of data that can be that can have a linear dependency towards your target variables. So you can adjust the data to that and create new features from like one-hot encoding and stuff. And general sense, just your usual like if I ask you as a human, like what would help you to solve this task, what would you include? So just general sense. So those are just 3 ways how you can think about generating your features when you try to brainstorm it, I think. So let me just give you a few examples of generating the features. Yet again, very few examples. In Data Science Olympiad, I do strongly encourage you to get a team and to work with a team. And so every member of the team would have his own ideas. So you would experiment with all your ideas and maybe stumble upon some feature that would increase your score a lot, or a bunch of features. So my first example is to add just simple polynomial features. So what are polynomial features? Polynomial features are those features created by raising existing features to an exponent of some degree. So for example, if a data set had one input feature X, then a polynomial feature could be the addition of a new feature column. So you can just calculate the new feature by putting X in power of 2, for example, or some other powers. So this process can be repeated for each input variable in the data set, creating a transformed version of each. What is the pros of creating polynomial features? Well, by generating polynomial features, we can help our model to uncover potential new relationships between features and the target, and to improve the overall model performance. Yet again, be very careful with multicollinearity and overfitting if this is the case in the models that you're using, but it can improve it a great deal, so that is true. I think that I have said pretty much everything about that. Another great example is date and time. So you can get a ton of information from date and time, but you do have to keep in mind some general sense. So for example, from date and time, what can we get? We can get the year, the month, the week, the day of the year, the day of the week, the overall number of the day, hour, minute, second, just components. Then you can use Boolean flags. So is it the year start or the year end? Is the month start? Is the quarter start? Is the quarter start has actually helped me in some cases. So a lot of examples. Is it the weekend? Is it the national holiday? Is it the, I don't know, the specific holiday for your country where the sales of certain products may rise, for example. Time differences, you can also calculate them. So difference in days, quarters, months, weeks, years, and so on. In Boolean flags, you can also use Boolean flags with not the date, but the time. For example, is it the rush hour? So like 9 a.m. in the morning and like 6, 7 p.m. in the evening. What else? The next thing would be various aggregations. So you can also do that various aggregations with date and time. So for example, take like the sales with combination by month. And maybe the feature of the categorical feature with like a combination of those would be better performing than those features by themselves. So various aggregations is this is one example of what I mean. Or here we have like this type of thing. So we have like users, we have cities, and we have visit days. So we can aggregate it by user and get the visit days by city, and then transform it in a new variable. So just different group bys, yet again, in a lot of cases, it can help you a great deal and can be a very, very useful feature. Moving on, I think that is all, because for feature generation, yet again, you can also calculate like a lot of the statistics. So for example, if you have like some kind of time series, so you can calculate like the mean for your time period for certain time period. You can calculate a lot of other statistics like maximum, medians, and stuff, and a lot of features can be used just by those few things. For me personally, they have improved the score in some competitions for a bit, but not a lot. But they did improve, so I do recommend it. So yeah, a feature generation, I do recommend you to pay a lot of attention to it. In most cases, this is what allows to get your solution from like just a bit above baseline to the top 10 solutions. Moving on, what else? And I have only the third part of my lecture left, would be to talk about feature selection. Just a very quick overview. I'm not going to dive into the maths behind it, so let's talk about it. The first one would be univariate feature selection. And for example, it is a model called select k best in sklearn. So select features according to the k highest scores. And the scores here would be the default ANOVA F value, but you can tune it and change it from ANOVA F value to something else if you can see fit. So just get the score for all the features and select these scores. And here is just a quick reminder of how to calculate the ANOVA F value. Another way to select features would be recursive feature elimination. And you would think it's dumb, but if you're not participating in a hackathon, but rather a competition which is held like for a month or more, then you can use longer ways to determine which features are the most valuable to you, like recursive feature elimination. The process here is very, very simple. It's as simple as the name sounds. So you train the features using some kind of model. Here it says random forest, but it doesn't have to be random forest. Gain the importance of every feature. Well, if you know sklearn, somehow it gives you it estimates feature importances for stuff like linear regression and logistic regression. It would be the weights. And for other models, there are other ways to estimate the feature importances. So it removes the least important features and calculates the classification accuracy of the feature subsets of the remaining feature subset, and checks whether it is empty or not. And if not, it removes the least important features. And if yes, you have your rank of features. So you just remove the least important features one by one, and you get the total ranking from the features you have removed last to the features you have removed first, because they were the least important. So this is how the recursive feature elimination would work. And another example is model-based feature selection. So this is a select from model in scikit-learn, for example. So it takes the model's coefficient or feature importances and selects features from those. And how does it work? Well, it has a certain threshold, which you can, of course, change. And the features that the importance says of which would be below the set threshold would be removed as the weakest, as non-important. So that is the three ways to use just built-in sklearn methods. And of course, I think I have forgot to mention it, but I think you do understand why we need a feature selection. Because after a long day of creating and generating new features, of encoding new features, adding them to your data, you of course do need to check out whether you need it at all. Because if you don't need it, and if they don't give any information to your model, then you are just wasting time, because the models are training longer, because you have more features, and those features are pretty useless. So you, of course, need to do the feature selection step after you have created some features to understand just how, even if you don't want to remove any features for some reason, it's still good to understand which features are giving the model the most information, because you can work from that point and just add more features like those ones. So yeah, the three ways: univariate feature selection, like select k-best in sklearn using default ANOVA f value. Recursive feature elimination, just eliminate the least important until you don't have any features left. And model-based feature selection, select from model in sklearn that use, for every model, there is like feature importances attribute that you can use, and it checks whether the value is below the set threshold. What else? Um, yeah, besides specifying a numeric threshold, you can also use the built-in heuristic to find a suitable threshold by specifying a string parameter. And you can also use the following heuristics. You can use the mean, median, multiply them by floating point numbers, like for example, 0.1 multiplied by mean, and stuff like that. So yet again, your creativity and your imagination is your limit. You can change it and tune it as you see fit in a lot of different ways. And of course, there are some standard ways that are taught in basic machine learning courses, like PCA and maybe TSNE for dimensionality reduction. So PCA just takes your data and somehow projects it to the things that are called principal components. So we have like one and two. So we have two of those, and it reduces dimensions like that. If you are not familiar with PCA method, I do strongly suggest you to take a few courses. So maybe join the Elena's program, a master's program at High School of Economics, or just yeah, online courses, or the book, for example, like the classics like Bishop and the machine learning like patterns and stuff. So yeah, if you're not familiar, then I do strongly recommend you to get familiar with this method before the Olympiad starts. I have already also said something about TSNE method, but for me it was always about getting the visualization of the data, of the multidimensional data in the two-dimensional space, rather than actually, like I did not see many solutions that actually use TSNE for like the dimensionality reduction. It's usually used for visualization, but you can also try it out, I guess. Just for me, I'm sharing this experience with you that I did not see it used many times in competitions or in real world. And I would like to leave you with a few things today. So I think it's really cool that we have this bootcamp that allows you to hear some of our lectures and to get some of our experience and to prepare for the and to try yourself out in the real world competition. So that is all very cool. And I think it's very great that you have started preparing in advance, because I think you do need to have to make certain steps before you enter such a competition. And some of those steps are here. So first of all, you can check out the winning competition solutions. So if you have the data description, which is almost never before the competition starts, but if you do understand what kind of task you will be given, then you can search for similar competitions and check out the ways people solved it. Or and you can also use archive.org or Google Scholar and look for the interesting articles, papers there. So that is one way to prepare yourself for a competition like this. Just to check out the papers, check out the similar Kaggle competitions and their solutions, because in a lot of times people who win the competitions, they do share their solutions in the code section of the competition. And yet again, there are other platforms besides Kaggle. For example, Zindi. A few years back, I think a year or two ago, it did have a lot of tabular data competitions. So in my opinion, like Kaggle a few years ago did not have much tabular data competitions, but Zindi had. And if you want to practice, I do recommend you this platform. I did check it out this morning, and there was like less tabular data competitions than the last time I checked it out. But I still do strongly recommend you. It's a nice platform, less money than Kaggle, less popular than Kaggle, but still a very good place to practice for the Olympiad. What else? For me personally, and for other people that I have talked about participating in different machine learning hackathons and competitions, another great advice that I heard was to write some code in advance. So if you want to generate like some features, you can write some code that generates like the basic aggregations before you start the competition. And when you start the competition, yes, you can modify your code a little bit, but the most of it is already written. Or you can write your code that helps you to validate the model beforehand, like the pipeline for model validation, another useful tip. So I have seen people do that, and of course, this is advice mostly for hackathons where you have limited time, and having some code written before would be a very good lifesaver. But for our IDAO, I think if you are starting to prepare now, you can also do that and save some code. So when the competition starts, you will be more focused on determining what kind of experiments you want to conduct, rather than just trying to write working Python code. So I think that is probably it for me today. Thank you for your attention. And now I will try to look through some of the questions in the chat. I have seen that there was a lot of messages, so I apologize in advance for not being able to answer all of them. So I will just try to get the few out. Oh, thank you for coming. Ildus says that we also have various HSC computer science courses available at Coursera, and we do strongly recommend them as well. You get the info in the Telegram chat, for example. Is there ways to assign a particular? I think there is. I'm just, so Mohamed asks if there are ways to assign weights to words in our bag of words model. So when you create this model, you just create some kind of table. After that, you run some kind of machine learning model. So it can be just, I don't know, simple logistic regression, for example. And simple logistic regression would actually assign weights for you. So I don't think that it should be done at the step when you are creating your table with the text and table with the words and vectorizers, because you have in my example, it was like 4 sentences, like 6 words, but in real world, it would be like 20,000 features, and you cannot assign weights manually. So if you want to do that, I do strongly recommend you to just run a simple baseline model that will assign weights for you. So that is what I can say about that question. Yes, we will provide the material, and on GitHub page, I think we'll send it to you after all the lectures today. I see a lot of overall. Yes, Mohammed also states that there are predefined sets of stop words present in NLP libraries like Analytica. Yet again, a very useful thing that I would like to point out. Thank you, Mohammed. That is a very good comment. How can we decrease the dimensionality in our solution was a question like half an hour ago. I think we have already answered it. Well, yeah, I think actually a lot of questions, as I see here, you had like a wonderful discussion where some people asked questions, some people answered it, and I think it's very cool that you had that. Maybe you get to know each other during these discussions while we have our lectures, and maybe create a team for our competition or for the IDEA one. So I think we have got most of the questions out of the way. So I think, yeah, that's it for me, Sergey. I think it's time for us to have a little break.
Anastasia, thanks a lot for your wonderful lecture. And I'm delighted to see that there were a lot of responses and questions and communication. So thanks again. Okay, guys, basically our next lecture starts in 15 minutes. So 1:30 p.m. Moscow time. So, well, basically, let's have this break. Otherwise, you can just chat either here or on Telegram. Yep. Oh, or for instance, if you have any questions to me, I'm also available. Will there be recordings? No, we do not plan to record so far. So yeah. Yeah, by the way, like they've been mentioned IDAO a couple of times. Basically, we open registration next week. And yeah, maybe after the bootcamp, you would be also interested to join in. Anyway, we will send to you all information when it's open in a couple of days. regarding the presentation, I guess that we'll put together a folder with all presentations and basically share it with you. So yeah, in order not to bombard you with many messages with like separate presentations, I guess it would be better if we collect them all in one place and send it to you.
Hello. Can you hear me?
Yes, we can, Elena.
Great. So let's start. 1 minute, please. Okay, my name is Elena Kantonistova. I am a lecturer at Higher School of Economics and academic supervisor of master's program, Machine Learning and Data Intensive Systems. My talk today consists of 2 parts. The first part is theoretical. During this part, I'll tell you what gradient boosting is and show some formulas. Also, we'll discuss some popular gradient boosting implementations like CatBoost, XGBoost, and LightGBM. The second part of my talk is practical. During this part, I'll show you some Python code that does feature engineering, feature selection, and of course, some modeling. And if you have any questions during my talk, please write these questions in chat. I'll try to answer some of these questions, and our assistants also will answer these questions. Okay. Okay. But before I start my explanations, please put a plus sign in a Zoom chat if you know what is gradient boosting and how it works. Otherwise, put a minus sign. Okay, I see. Good, very good. Many of you already knows what is gradient boosting and how it works. But anyway, I will explain you the key idea of boosting, or for someone, I remind you the key idea, and I'll show you some formulas, of course. So let's start. Gradient boosting, it is a machine learning algorithm that we usually use for classification or regression. It is an ensemble or composition of multiple weak learners, BI. Usually, each weak learner, it is a decision tree. Do you know what is a decision tree? Yeah, that's great. Boosting, it is an ensemble of decision trees. And it has a formula that you can see on this slide. Boosting A of X, it is simply a sum of decision trees. But the important thing that in gradient boosting, we build trees not simultaneously, but step by step, and add them to the composition. Let's look at the next slide. Here you can see the key idea of how boosting works. So it is the following. At each next step, we look for a decision tree that corrects the error of the composition in the previous step. Let's look at the picture. So at the first step, we built the first decision tree that solves our task, classification or regression task. It doesn't mean. So the first tree solves our task. If it is not overfitted, it has some big loss, big error. Then on the second step, we build the next tree in such a way that it corrects the error of the first tree. And then we add this tree to the composition. And since the second tree corrects the error of the first tree, the total error of the composition will decrease. And so on. On the third step, we build the third tree in such a way that it corrects the error of the previous composition. And then we add this tree to the sum, to the composition, and so on. Did you understand it? Did you get the idea? Good, good. I'm happy to see it. So let's go to the next slide. You can see here some formulas that describe the same process. Let's say that X is an object and Y is a target. It's an answer. Then boosting builds a composition of trees one by one. And then the predictions of the individual trees are summed, as we discussed. For example, after the second step, our boosting has two trees, B1 and B2. And formula for boosting after the second step, you can see it here, A is equal to B1 plus B2. Then on the next step, we built decision tree B3 in such a way that it predicts the error of the previous composition. That means that we change the target. So the target for the tree B3 will be the error. The error, it is just the difference, correct value Y minus prediction of composition, minus A of X. So Y new, it is the error of the composition, and it is the target for, for new decision tree. So we build decision tree in order to predict this target, and then we add this tree to our composition, and so on. I think that's it with the formulas for classical boosting. Also, I want to show you another example of boosting, of how boosting works. By the way, what do you think? What type of task shown on this slide? Is it a classification or regression task, maybe clusterization? What do you think? Yes, most of you are right. It is a regression task. Let's look at the left upper image. Black points here are our data. Each point has one feature, X, and the target value is Y. So it is a regression task. And we want to solve it with boosting. At first step, we built the first tree, the first decision tree, to solve our task. And the first tree, it is a green curve here. We can see that this tree solves task not good because there are some points with a big error, prediction error. For example, these points in the right circle, they have a big prediction error. And then for each point, we calculate the error of the first tree. It is simply the difference, Y minus prediction of the first tree. And you can see a new set of points on the left lower image. These black points are the errors of the first tree. And then we built the second tree, the second decision tree, to predict these errors. You can see a second green curve here. It is a second decision tree, and it predicts the error of the first tree. And then finally, we add these trees. and we get this blue curve. It is boosting that consists of two trees. And you can see here that blue curve approximates our points better than only the first tree. So boosting works. I see your question, but making trees again and again wouldn't make the complexity very high. Yes, of course, when we add to our composition more trees, it becomes more complex, but it's not a big problem. It's just a property of boosting. We can regulate it. I'll tell you further. Okay, so that's it with classical boosting idea. And you can see that gradient boosting, it is a very powerful algorithm. And you can achieve good quality, high accuracy in your tasks when you use boosting. But gradient boosting likes to overfit. That means that more trees you add to the composition, then the train error will decrease. You can see it on this picture. Blue line, it is a train error, and it decreases when we increase when number of trees increase, and it's okay. It's how boosting works. But starting from some certain number of trees, the test error will increase. And here the overfitting starts. Here we can see that test error is minimum at when a number of trees is about 63 or 64. That means that if you want to achieve a good quality, then you need to find optimal number of trees in boosting in order to minimize test error. Test error is more important than train error because test error, it is the error on a new data. Do you have any questions maybe? Is it very difficult? What do you think? Good, let's continue now. Now I will explain you how some modern implementations of boosting work. There are lots of implementations of boosting, including classical implementation of gradient boosting in SciPy Python library. Each algorithm grows trees differently and uses some complex theoretical facts. I'll tell you key ideas of each of these algorithms without going into details. If you want to study these algorithms in details, I'll provide you with links on the topic, and you can read papers via these links. So let's start from this timeline. You can see that the first powerful implementation of XGBoost appeared in 2014, 7 years ago, but actually it became famous and widely used in 2016. Tianqi Chen invented XGBoost. Then in 2017, LightGBM and CatBoost appeared. Microsoft released LightGBM, and Yandex researchers invented CatBoost. I see your questions. We can use gradient boosting for regression and for classification tasks. So if you want to know how it fits in details, please read my links, read information via links. So let's start with XGBoost. It's our first client here. And since XGBoost was the first powerful implementation of boosting, I will compare it with classical boosting. XGBoost, it is an improvement of classical boosting. And it has two key features, two key differences. And the first one is it can be a bit difficult. So the first feature of XGBoost is when we constructing each decision tree, the loss function in XGBoost is approximated to second order. But in gradient boosting, it is approximated to the first order. That means that XGBoost solves your task more accurately than classical boosting. And the second feature of XGBoost is that it uses regularization. By the way, who knows what regularization is? Please write in chat. What is regularization? Yes, you are right. Regularization, it is a special technique that we use in machine learning in order to prevent, to reduce overfitting, I would say. So in XGBoost, we use two different regularizations. The first regularization penalizes the tree for the number of leaves in it. You can see it in the picture. So with this regularization, decision tree will have a smaller number of leaves than without it. And the second regularization is quite tricky. It penalizes the tree for large forecasts in the leaves. You can see the example here. It has sense because trees in gradient boosting, they predict the error of the previous composition. And this regularization makes these predictions smaller than without this regularization. So that's it. That's the second key feature of XGBoost. And with these regularizations, decision trees in XGBoost, they overfit less, and that's a profit. Again, the first key feature of XGBoost is that it solves our task, classification or regression task, more accurately than classical boosting. And the second feature is that we reduce overfitting using a regularization technique. Okay, let's go to the next boosting. Here you can use these links. The first link is XGBoost documentation, and it consists of all the theory. You can read it. The second link also tries to explain XGBoost theory. And the last link, it combines theory and practice with XGBoost in Python. So let's go to the next boosting, CatBoost. CatBoost is the first Russian machine learning algorithm that is open source. It was created in 2017 in Yandex. What? Okay. I think that you don't like my questions, but I want to answer some questions. I want to ask some questions. Please write in chat if you know why CatBoost called CatBoost. Is it related to cats? Yes, it's a good idea. Lots of good ideas. Yes, it's related to categorical features. Let's talk about it. So main advantages of CatBoost are the following. It has very good quality on many data sets. It has high prediction speed. It supports for both numerical and categorical features. That's why it's called CatBoost. And it has a fast GPU support. This boosting works so well because of three key features. I will tell you about these three features, but without going into details. Let's start. So the first key feature of CatBoost is that it uses asymmetric trees instead of classical trees. You can see it on this picture. On the left side of this picture, it is a classical tree for some task. It can be balanced, it can be unbalanced. We don't know in advance. But symmetric tree is always a binary balanced tree. You can see it on the right side of the picture. And let's see, on the second level of this tree, in both vertices, we check the same condition. It is not a mistake. So it means that if a person's height is greater than 170, we go to the right vertex and we check its weight. We check if its weight is greater than 65 or not. But if a person is less than 170, then we go to the left and we check the same condition. We check if its weight is greater than 65. And so on. If we want to grow our tree further, then in the third level, we will check some same condition in all four vertices. For example, we can check if age of a person is greater than 30. So in all these vertices, in four vertices, we will check the same condition. So it is a symmetric tree, and CatBoost builds symmetric trees. So symmetric trees, they overfit less than standard trees because of the fixed structure. I will explain. Let's say that we slightly change the training data. Then the classical tree will can totally change its structure. But symmetric tree will not change its structure since it's fixed. That's why it overfits less. And also, thanks to symmetric trees, CatBoost shows good quality even with default hyperparameters. And that's a great feature. You don't need to spend a lot of time to tune your boosting and to find hyperparameters to achieve good quality. So of course, you can tune your CatBoost, but even with default hyperparameters, boosting works well. Next key feature of boosting, that it can encode categorical features itself. Nastya already told you about categorical features, I think. So we have numerical features that are numbers, and we have some features that are not numbers, like a person's occupation. It can be gender of a person, city of living of a person, and so on. It is some feature, but it's not a number, and we need to convert this feature to a number using some technique. And there are lots of approaches how to encode categorical features. And of course, you should spend time if you want to find an optimal encoding for every categorical feature. But CatBoost can encode categorical features itself during training, not before training, but during training. It tries to combine different encoding techniques. It uses one-hot encoding, different target encoders. It also uses encoding based on permutations of features, and it has combinations of encodings. So you don't need to spend time to find optimal set of encodings for every feature in your data set. CatBoost can do it for you. Okay, I will read your messages. Okay, so let's go to the last key feature of CatBoost. I know that this material can be a bit difficult, but I try to give you the key idea of all these features. And if you want, if you are interested in details, there are links, and you can answer questions. I will answer these questions in chat after the talk. Okay, so the last key feature, the third key feature of CatBoost is that it uses ordered boosting. What does it mean? Classical decision tree overfits a lot, because when we build decision tree, we use the same data to find tree structure and to make the predictions in leaves. And so that's bad. Machine learning tells us to use different data sets for fitting and for prediction. But in decision tree, we use the same training data to build the tree and to make the predictions in leaves. That's a problem. Ordered boosting does some tricky procedure. In every leaf of the tree, we randomly permute the objects in this leaf and make a prediction in the leaf based on this random permutation. So this adding randomness in the process of making the prediction reduces overfitting, and that's why boosting is more stable. CatBoost is more stable to overfitting than classical boosting, and then XGBoost also. So that was the last key feature of CatBoost. And there are some links. The first link is a CatBoost documentation. The second link, it is a video presentation of CatBoost by developers. It's a very good video. I suggest you watching this video. And the last link explains theory and CatBoost practice in Python. So, and the last boosting that I want to discuss with you is LightGBM. It was developed in Microsoft Research, and it is also an open source library. It also has a lot of advantages. It's called light because of high speed. It's high speed. It can handle large size of data. It also has a very good quality on many data sets, and it also supports GPU learning. LightGBM works so well because of its two key features. The first key feature is how LightGBM grows trees. It grows trees level, not level-wise. So usually boosting grows trees level-wise. It means then at each step, you add a new level to your decision tree. But LightGBM grows tree leaf-wise. That means that at each step, it adding one leaf to your decision tree. It will choose the leaf with max delta loss to grow, and this algorithm is more accurate. It predicts target more accurately than classical decision tree that we built level-wise. So, and the last feature, the second key feature of LightGBM, called feature bucketing or feature binning, if you want. So what does it mean? It unites similar, let's say that we have some numerical feature with a lot of values. So feature binning, it is a technique that unites similar values of features in bins. This technique based on some histogram algorithm. And because of this feature binning, we have two profits. The first profit is that our new feature, binned feature, has less values, and that's why we fit our tree faster. And the second thing, since we united similar values in one bin, we reduced noise, and that's why we reduced overfitting. That's how it works. That's it with theory. Now let's go to practice. I will show you some Python code that demonstrates how to work with features, how to use these boostings. I will answer your questions later because I don't have a lot of time now. Sorry. So let's go to practice. I will show you some Python code in Google Colab. 1 minute, please. Also, now I will send you a link. You can open this Python notebook on your local notebook on computer. So let's go to the code. In this notebook, we will do a lot of things, actually. We will do exploratory data analysis, then we will train lots of pipelines to solve a classification task, and then we will use CatBoost for modeling and to encode categorical features. In this notebook, we'll work with a data set about Pokemons. So let's upload this data set to Google Colab. I will do it using Colab interface. Okay, and let's look at the first cell with the code. Here we import some libraries, pandas for working with data frames, NumPy for effective calculations, and matplotlib and seaborn for visualization for plotting graphs. Let's run this cell. Then we will ignore warnings. And now we read our file, our CSV, with the information about Pokemons. Let's look at this data set. Here you can see the information about different Pokemons. It's a Pokemon name, type of Pokemon, type 2, and then some stats, some Pokemon stats. And our target column here is the last column, legendary. Some Pokemons are legendary and some are not. And we want to make a classifier that will solve our task, that will predict for every Pokemon if it's legendary or not, using its features. You can see that there are some non-values. For example, for Charmander, there is a none in a type 2 column, but that's okay, because some Pokemon, they don't have type 2. And in this case, there is a non-value. That just means that this Pokemon doesn't have type 2. Okay, so let's look if there are other non-values in our data. No, you can see that we have not a number of values, only in one column, type 2. That means that these Pokemon, they don't have type 2. And let's fill these non-values with a new category. Let's fill it with a category no second type. And that's it. We also drop 2 columns. The first column, it's just a number of row. It's not important. And also we will drop a Pokemon name. It's also not important for us. Now, we should form the data for machine learning algorithms. We need 2 objects. It's a matrix with objects and its features, X. This matrix should not contain the answer. That's why we drop column legendary from this matrix. And we create a target vector Y. It contains the answers if a Pokemon legendary or not. Also, let's look if our task is balanced or not. And we can see that it is not balanced. Most Pokemons are not legendary. The target value is 0. And about 8% of Pokemon are legendary. The target for these Pokemon is 1. The next chapter here, it is exploratory data analysis. It's a part when we plot graphs, when we try to find some dependencies on our features or between features and target visually. This part is of course very important, but I will skip this part. You have all this code, you can study it, you can ask questions, I will answer these questions, but my point is today I want to show you how to create different models, and I will skip this part with the different visualizations. Now let's create some machine learning models to make predictions. And I will tell you about pipelines. By the way, who knows what is a pipeline in Python? Okay. I will explain these concepts briefly, but I'm happy that you most of you know what is a pipeline. So pipeline constructor in Scikit-learn allows you to chain transformers and models together into one fat model. So for example, if your model involves feature selection, standardization, and then some model, you can unite all these steps in one big pipeline. It is a one big model. Let's look at the picture. It is an example here. So in this example, at first we do scaling. We scale our data, then we reduce dimension, and finally we apply some model, machine learning. And we unite all these 3 steps in one pipeline. Since it is a standard model, it has 2 methods, fit and predict. We fit our pipeline on the training set, and then we make a prediction. We can make a prediction on the test set. Yes, so let's create our first pipeline. It will be our baseline. It consists of 3 steps. The first step is encoding of categorical data. We will use the simplest encoding, one-hot encoding. Then we will scale our data. And the last step is to apply, we will apply some simple linear model for classification. By the way, what do you think? What is the simplest classification model in machine learning? Naive Bayes, linear regression, linear classification, constant. Yeah, maybe the simplest model is constant. I'm agree with you. Okay. Also, we install library category encoders because it contains a lot of interesting category encoders, and we will use it. So now let's create our first model. We import a pipeline tool, one-hot encoder, standard scaler. We will use logistic regression. It is not the simplest classification model, but it's quite simple, and we will use it. And we will evaluate the quality of our model using cross-validation. So let's look again at our data. What do you think? How many categorical columns do we have here? You think 3 categorical columns, or 2, or 4 categorical columns, 10. That's interesting. Actually, we have here 2 categorical columns. This is column type 1 and type 2. They are obviously categories since it's not numbers. But our last column, it's a target, and it's binary. It consists of true, it is equal to 1, and false, it is like 0. So we have only 2 categorical columns, type 1 and type 2, and we need to encode these columns. So let's go to our pipeline. So our cat calls are here. It's type 1 and type 2. And we create the first pipeline, the first model. The first step here, it is one-hot encoding. We encode categorical columns. Then we scale our data, and we apply a classification model, logistic regression. That's it. Now we can evaluate the quality of our model. We will use cross-validation. The first argument here, it's our model, default pipeline. Then we put here our data, matrix with features X, and Y is a target vector. Then we will use 5 folds, and we will use scoring, we will use matrix F1. By the way, can we use accuracy metrics here? What do you think? Can we type here accuracy? Yes, you're right. I'm very happy that you listen to me. Yes, that's correct. We have imbalanced data set here. That's why accuracy isn't a good choice. But F1 score is a good choice for this task. We will use it. F1 score has values in between 0 and 1, and if it's close to 1, that means that your model is good. Otherwise, your model is bad. So let's look at the mean test score. It is 0.44. I think it's quite bad, but it's only our baseline model. Now let's improve it. And there are different ways to do it. The first way is to use other categorical encoder. There are lots of categorical encoders. Nastya told you. You can use leave one out encoder, target encoder, weight of evidence encoder, and so on. There are lots of categorical encoders in this library. You can try all these encoders. The second way to improve quality is to create new features. Maybe we can create new features that will help our model to find dependency of target on our features. The third way to improve our model is to select important features. I will tell about it later. And the last step that we can try different models, not only logistic regression, maybe KNN or decision tree, and of course we should try random forest and different boostings. Is it okay to scale transformed features? Yes, it's not a problem. Yeah. Let's start. So the first step is to try different categorical encodings, not only one hot encoder. Let's import leave one out encoder, target encoder, and maybe weight of evidence encoder and mean estimate encoder. Let's try these encoders. And we will try these encodings in cycle. So there are 4 types of categorical encoders. We use the same pipeline, you can see it, but on the first step, we will try different encoders. And we will evaluate the quality of our model in cycle, and we will print the result. Let's see. Yes, one hot encoder is not the best option in this task, you can see it. But leaf-one out encoder works quite well. It has F1 score is about 0.59. That's good. And we will use leaf-one out encoder in our future pipelines. I think that that's in yes, it usually doesn't important, not so important how to scale your data. You can use standard scaler or min-max scaler on maybe min-app scaler. So that's not important usually. Why generation is not a categorical feature? Of course, yes. There are some generations, 7 generations of Pokemon, first generation, second generation, and so on. And so we can compare these numbers. So second generation is, in some sense, it's greater than first generation. We can compare these numbers. That's why we can use this column as a numerical column. So let's go to the second step. So now we checked the different categorical encodings, and we understood that leaf-one out encoder is the best option here. Then let's add new features to our task, because we have about 10 or 11 features here. That's not a lot, and we can create new features. Here we will use a polynomial features tool from Sklearn. So how it works? It creates all polynomial combinations of the features with a degree equal or less than the specified degree. For example, if you have 2 initial features, x1 and x2, and if you want to create polynomial features of degree 2, then you'll get features 1, x1, x2, x1 squared, x2 squared, and x1, x2. So the method, it created polynomial features of degree 2 and less. Yeah. So let's create new polynomial features in our task. We will create a lot of features, really a lot. So we add in our pipeline new step. So the first step is categorical encoding. It's leaf-one out encoder, since it works better than other encodings. Then we create new features. We use polynomial features of degree 4. Then we scale our data and we apply our model logistic regression. Let's look if polynomial features help. Let's evaluate our model. What can we see? Test score increased. It was 0.59, now it is 0.60. But train score here is close to 1. That means that now here we have an overfitted model. So train score is close to 1, but there is a big gap between train and test score. What do you think? Why we have an overfitted model here? Why we have this problem here? Yes, we created a lot of features. We added features of the polynomial features of degree 4. That's really a lot of features. That's why we overfitted. Let's see how many features we have. I will not explain these cells to save time. So let's see. We have 800 Pokemons, 800 objects, and 1001 features. That's a lot. So that's why we overfit. but maybe we have created some important features. That's why now we will select important features. And we start our third step here. We will apply different feature selectors to reduce our feature dimension. That's a lot of features, yes. So what is feature selector? So we have a lot of features. Yeah, then we use some method that removes some not important features according to this method. And we have a smaller set of final features. I hope that Nastya also told you about feature selection. Did Nastya tell you about feature selection techniques? Good. So the first way to select features is to use univariate feature selection. Great. So univariate feature selection, so it's, I would say that it is a generalization of correlation. So you can calculate the correlation between the feature and target value. And you could say that if correlation value is high, then there can be some dependency between your feature and target value. Yeah, but you can use other statistical tests except correlation. Here in Scholar, there is a select K-best tool that we use for univariate feature selection. It selects K-best features. Then you should select statistical test according to which you will select your features. It can be correlation. It can be something more difficult, more interesting. It can be F classification statistics, H squared, maybe mutual info classification. Here we will use mutual info statistics. Let's try to select features now. Let's say that we want to select 20 features. Then we add to our pipeline a new step. So we have categorical encoding, then we create new features. Now we have lots of features. Then we scale our data, and then we select K-best. Here it is 20 best features according to some statistics. Here it is a mutual classification. And then we apply our model. So let's see. But I need to say that 20 here, it's a random number. You need to choose this number carefully, maybe via grid search, if you want to achieve good quality. You can see here that test score is about 0.51, and train score about 0.62. So we removed overfitting, but the quality of our model is not high. So let's try other feature selection technique. It is a recursive feature elimination. So we take some model and it recursively removes some unimportant features. In Scholar, it is a RFE tool, recursive feature elimination, and we will use logistic regression to select features. So we change this step. Now we use other technique for feature selection. It is a recursive feature elimination. It can work sometime because recursive procedure take a lot of time. Thank you for your message. Yeah. So we can see that the quality of our model with leaf-one autoencoder, polynomial features, and then recursive feature elimination is quite good. F1 score is 0.67. Yes. But there are other techniques for feature selection. Maybe they will work worse in this task, but I want that you know about these techniques, because we don't know in advance which technique works better in some particular task. So the third method to select features is model-based feature selection. We can take some model, we can fit our model in our data, and then we can select only those features that have the biggest weights. And we remove the features with smallest weights. So let's use this option. It is a select from model option in Sklearn. We also will use logistic regression to select features and then for modeling. So at first we select features using this model, and then we predict something using logistic regression. So let's look at the result. Here we can see that the quality F1 score is 0.63. It's worse than in recursive feature elimination, but also quite good. We can change logistic regression to maybe random forest or to boosting, and maybe the quality will increase. You should try all these options. It's only the demonstration of method. And the last method to reduce a feature space, it's not a feature selection actually. It's a method of dimensionality reduction. It's called principal components analysis. It works quite tricky. There is some linear algebra inside it. But let's try to use it also to reduce feature dimension. We import PCA, a principal components analysis, and we will use it to reduce number of features. So we change this step. Guys, I need maybe 5 or 6 more minutes. Is it okay for you? Okay, thank you. I see your question. The feature selection also decreases the dimensionality, yes, but there is a big difference. Previous feature selection methods, they removed some features, and that's why we reduced the feature dimension. But PCA, it creates new features. It doesn't remove some features. It creates new features. But the number of new features is smaller than the number of initial features. So it's other approach. It's not a selector. It creates new features. So let's try to use this method. It is here, PCA. For demonstration only, let's select 5 new features here. Not a lot, but let's do it. So we can see that with principal components analysis, we have 0.56 F1 score. Not a lot, but again, you can change this number. Maybe you'll have higher quality of your model. So, and the last step, we need to try. We can try other models. We used only logistic regression, but we can use CatBoost, HexaBoost, LightGBM, since we discussed it in the first part. The first thing is to install these libraries. It's not difficult. Just type pip install and the name of your library. And then let's try lots of models in cycle. We will try SVC. Who knows what is SVC? Yeah, that's great. It is a support vector machine. It is also a linear classifier, one of classical classifiers for machine learning. Also, we will try K-neighbors classifier, and we will try something more complex. It will be random forest and classical gradient boosting. And of course, we need to try use CatBoost like GBM and XGBoost. We will try all these models in cycle. So here is our pipeline. It contains categorical encoder, polynomial features, then scaling. Then we use select from model to reduce feature dimension. And the last step is our model. And we will try different models in cycle, and we will estimate their quality using cross-validation. So let's see. So you can see the name of your model and the score. And surprisingly, random forest and gradient boosting, they work worse than SVM or logistic regression. And even XGBoost and CatBoost have bad quality here, you can see it. But that's actually not a problem, that's a feature here. Because if you want to get a high quality, you need to tune your models. You need to find optimal hyperparameters. But since we don't have time, I will tune only CatBoost. So let's give a chance to CatBoost, because I like cats. That's why this is the one model that I choose. So I will split my data into train and test, and then I will fit model, CatBoost model on train for different number of estimators of trees, and I will predict on test. So here there is a cycle. In this cycle, we try different number of trees of estimators, and we will plot graphs. There will be F1 score depending on number of trees on train, and F1 score depending on number of trees on test. And we'll see if it helps. So let's wait maybe 30 seconds, another 30 seconds, because we try from 10 to 1,000 number of decision trees. Boosting, we need to give boosting some time to fit all these combinations. But here you can see the result, but let's wait. By the way, there is a very convenient library. It's called TQDM, and it shows you the progress. You can see this progress bar, and I created it using TQDM library. So now we can see the result. So a blue line, it is the quality of our model on train. You can see that boosting has a quality of 1 on train, and it's okay. It's how boosting works. But on test, the optimal number of trees here is 60. And then we, so the quality doesn't increase. Usually boosting overfits when a number of trees is growing, but here in this task we can see that CatBoost doesn't overfit with growing number of trees, and that's great. But let's try here. We can see that optimal number of trees is 60. Let's put 60 here in boosting, and let's evaluate its quality using cross-validation. So now we found optimal number. We have found optimal number of trees in boosting, but it didn't help. So CatBoost have a very low quality. 0.5. You can see that the quality on different splits varies a lot, and that's a problem. So let's stop here and let's try the last chance to our boosting, the last chance. So we know that CatBoost can encode categorical features itself. Yeah. So let's try this option. We will not create any pipeline. So we will use only CatBoost, only one classifier here without pipeline. There is a list of our categorical features. So we have a categorical feature in column number 0 and in column number 1. And we ask CatBoost to encode these categorical features itself. So you can see the result. It has a quality 0.70. So CatBoost solved our task better than all previous pipelines. When we asked CatBoost to encode categorical features itself, it solved the task very good. So it is not a rule, no. So in your task, maybe some pipeline works better than CatBoost option. But you know, all these tools, you should try different approaches. Maybe CatBoost will work better itself without other steps. Maybe some complex pipeline will help. We don't know in advance. So here you can see that CatBoost has a very high quality, high F1 score. But now we can tune hyperparameters. And I think it's the last cell that I'll show you. The most important hyperparameters are number of trees, of course, and learning rate. And we can tune hyperparameters, for example, using grid search. It is the dictionary of our hyperparameters. And we here we found optimal hyperparameters. So we need to use 340 estimators and learning rate 0.05. And here we have a very high quality, 0.75 almost. So let's stop here. I showed you lots of pipelines, lots of information. I think that it will help you somewhere maybe, yes. But again, there are lots of approaches to work with data. You can encode data with different approaches. You can generate features, then select important features. You can use some complex model to do all this stuff like CatBoost or LightGBM or XGBoost. But you don't know in advance which model works better in your task. That's why it's good to try lots of these approaches in your task. So that's it. Maybe you have any questions now. In balanced learning, I think it's you can use imbalanced learning in the part of where you transform your features. So it should be the first or the second step when you transform features. Is it a good idea to select features by linear model and then to feed it to non-linear model? It might work. We don't know in advance. You should try. So, and I will answer the last question about degree 4. We use polynomial features tool from Scalearn, and we put here degree 4 in polynomial features tool, and this tool creates all polynomial features of degree 4. Okay, so guys, thank you for your attention. Now we have a break, and we will restart our talks at, let's see, it's 3 p.m. Yeah. So again, thank you. Bye.
So I think I'm ready. So I would appreciate if you, Sergey, could present me to the listeners a bit.
Yeah, sure. Thanks a lot again for joining. I guess pretty much everything is set on your screen that you're sharing now.
Yeah, sure.
And we're joined by our next speaker, Ildus Sadrtdinov. I hope that I pronounced it correctly. I trained a couple of times before the lecture. Okay. I'm giving up the stage to you. Yeah, Ildus is from HEC. He's a lecturer in intern researcher. So Ildus, the stage is yours. Thanks.
Yeah, thank you so much. I'm really pleased to see so much machine learners to participate at our bootcamp. And so I hope you'll learn pretty much new for today's lectures. But today I want to speak about something different. And this topic is usually not covered by the classical machine learning courses. So actually, I want to tell you about some non-trivial applications of machine learning, especially for some non-classical data examples. And to be more specific, I would like to stop on different techniques for processing tasks on graphs. So first, I would like to discuss what does actually our machine learning pipeline consists. So first of all, if someone wants us as a machine learning engineers to solve some tasks, this person gives us some data, and actually the data is something we cannot just take from ourselves. Usually our data is given to us, and we need to solve some tasks with regard to this data. But what we actually can modify in this pipeline is the algorithm itself, which is used for predicting different data. So there are a couple of examples of machine learning algorithms that are frequently used in different pipelines. And for example, this might be industrial pipelines or different data competitions. And so there are also different types of data we have to deal with. And usually our selection of the machine learning algorithm is related to the data we have to. So today I want to speak about different non-trivial examples of data. And so here are several examples that I could figure out. So the first one is different medical data sets. They're complex to process, as usually when you work with medical data, you have pretty much samples to work with. And these data is usually of different nature, for example, including different, I don't know, surveys of your patients, or I don't know, some MRI, for example. So this data is usually multi-domain, and this even complicates things more, as we have to use different algorithms of different nature to process these medical data sets. The different example is different interaction networks, because like the main difference of this scenario is that your data samples, they're not just simple rows of some column of some table. They're just they also have interaction between each other. Also, I would like to tell about molecules data sets. They are also complex because of their structure, as we not only have the atoms in each molecules, we also have different connections between them. And if we want to build a successful machine learning pipeline, we have to deal with these difficulties as well. So the other examples are DNA chains as well. DNAs are just enormously large chains of different nucleotides, and due to their size, it is often difficult to process them. And the last example of non-trivial data is different source code data sets. I think usually we can treat different source code as like an example of a text written in some weird language. Actually, the programming languages, but they're usually, it is also difficult because the the programming languages, they have more strict structure than regular natural languages we use. And so there is a main question, how to process these examples of non-trivial data. Usually we have some classical solutions which come from earlier works in these fields. For example, from biology or from physics, if we have some data related to different observations in these topics. And these solutions are usually suboptimal in the sense of the final accuracy, for example, that we get, because they use some heuristics that are far away from the optimal solutions which can be obtained by the machine learning algorithms. We often have some data specifics. ML algorithms, they're usually designed by machine learning engineers who tried to solve these tasks previously. And I would say that these solutions are often state-of-the-art and performing the best. But the main disadvantage of these methods is they may be rather complicated. And if you want to implement such solution in your competition, you will have to spend hours and days before it starts working. So probably this is not the best option for you to start your competition. And so there is the third option, which consists of feature extraction plus applying classical machine learning algorithms. And I think this is the point where we will stop and discuss it for the rest of our lecture. These algorithms are usually relatively easy to implement, as you just need to implement the feature extraction itself, and then you just use the algorithms you are familiar with. And I would say that this option is the best one for starting your ML competition in when you work with non-trivial data, because it is simple and usually it performs great. So it's, I think, the best option for the baselines. I would like to begin our talk with different data structures that we have to deal with. Probably the most easiest one is different sequences. They have clear 1D structures, usually related to the difference in time. This includes text, different audios, and other time series, like, for example, stocks. So a different example is 2D structured data, which usually consists of some kind of a grid. This is an example of different images that are quite often processed in computer vision scenarios. And different spectrograms. For example, we talked about MRI in medical data. So the MRI is the example of spectrograms which is used. But today I want mostly focus on arbitrary structure, and this is the point where graphs come into our game. Because actually, if you have a graph, you can define an arbitrary complex structure of your data. And if you are able to process graphs and train different machine learning pipelines on them, you'll be successful actually at any data, because despite its structure, you can just take your graph processing pipeline and succeed with it. So what actually is a graph? For those who are not familiar with these mathematical structures, usually we have some arbitrary set of nodes, might be anything, for example, I don't know, animals or machine learning papers or something like that. And we actually, what we also have is these connections between the nodes. I'll usually call these nodes, but sometimes I'll call them vertices, so don't be confused. We define different connections between the nodes, and this is our edges. And so any structure with different communication between the objects, we can describe it as a graph. So actually, on my slides, you will sometimes see these tables with notations. So if you for some reason missed what I say, you just can't you just can take this table and revise it. So a very important concept when we talk about the graphs is the adjacency matrix. It's one of the most popular ways to store your graph. This is actually a matrix with the size equal to the number of nodes squared. And this matrix actually stores the different connections between your nodes. For example, here we have an edge between vertices 2 and 3. And so here we have the corresponding elements in this matrix equal to 1. For example, if we have a weighted graph, we will have these weights stored in the matrix, not 1, but some arbitrary positive, usually positive numbers. And if we have, for example, a directed graph, when we have different, for example, the edge from 2 to 3 doesn't lead to an edge from 3 to 2. This is an example of oriented graph. And in this case, we'll have non-symmetric adjacency matrix because the elements of that are lower than the diagonal would not be equal to those upper the diagonal. So this is I think, the most popular way to describe a graph and to store it in the memory of your computer. Let us talk about different examples of graphs. So there are many of them we can figure out. For example, these are social networks when, for example, each user of this social network is a node, and the friends in the social network are, when they are friends, we have a connection between them. There is also a bunch of different knowledge graphs when you have some connections between different objects describing something in the world. For example, we know that Da Vinci painted Mona Lisa, and thus we have a node Da Vinci, we have the node Mona Lisa, and the relation between them is painted. So this is a kind of an oriented graph, and it is pretty obvious how to set this knowledge using a graph. More examples are, for example, transport networks, when we have different cities as nodes and connections between them as roads, for example, probably railroads or just regular automobile roads. And when we talk about molecules, they also can be represented as a graph because we have different atoms and the chemical connections between them is our edges. So we actually would like to solve different tasks which are related to the graphs. And so these tasks are divided into two groups. They might be either node focused or graph focused. When we stick to the node focused tasks, our object actually is a node itself. For example, we can have node classification if we want, for example, I don't know, to define different social roles in our social network graphs. This might be different determination of structure and relationship with respect to the nodes. Also might be some link prediction. For example, when you go to Facebook and it recommends to you to just add these guys to your friends, probably you're somehow acquainted with them. And probably the last example is the node recommendation, which I think is almost the same that link prediction somehow. Again, the example with Facebook works. And a different category of tasks is graph focused when your object is an entire graph. So this might be a graph classification. For example, you have different molecules and you want to predict whether this particular molecule is poisonous or not. So this is the example of classification. You also may want to generate some new molecules, and this is an example of graph generation tasks. And there might be also some global properties of the graph. I don't know, some probably chemical properties of your molecules, and so you may want to estimate them as well. And these are all examples of graph-focused tasks. And there are different like subtopics in graph machine learning which are possible to discuss. So I think the most common thing is supervised learning. When you want to predict some particular labels for graphs and nodes, these are different cases of classification and predicting other different properties of your graphs. The other case is reinforcement learning. When you interpret your graph as somehow something like interaction environment, for example, you have a board game, which is defined as a graph, something like, you know, these like dragons and letters, I think. You can interpret it as a graph, and you will have different agents which do some actions on this graph and probably interact with this environment somehow. This is what reinforcement learning is. Today, I want to mostly focus on representation learning, when we actually want to extract some informative features from the graph and store it as a high dimensional vector. And so we will reuse these features in our machine learning pipelines to solve the task we want to using classical machine learning algorithms. And probably the last type of tasks is generative models, when you want to take different molecules, for example, and generate a new molecule with a new property that you wish. So this is an example of generative models in graphs. So as I mentioned, I would like to focus on representation learning. The main aim of representation learning is to take an object of arbitrary structure, for example, a graph or a node inside the graph, and apply some transformation that would preserve the useful information stored in this arbitrary object. And so we'll get some high dimensional vector that is usually called an embedding, and we'll reuse these embedding later for solving different tasks, for example, at our machine learning competitions. So I would like to start with the embedding nodes, when our object is actually some node in the graph, and we would like to get a vector representation of the node to reuse in further tasks, for example, node classification or structure role classification. To start with, we need some mathematical properties of the graph, and I want to define something called proximity measure. This is something which defines whether two nodes of the graph are distant from each other. So, for example, I can take simple graph distance in the sense of the number of edges lying from one node to the other. And in this example, I have distance 1 between this blue and this cyan nodes, and distance 2 between this blue and this pink nodes. And so actually we can measure the proximity of the nodes using simple distances which can be defined on our graphs. So I think nothing complicated in this sense. And what we can do to define our algorithm to encode embeddings, we can try to approximate this proximity between different nodes. For example, we can consider this encoder-decoder approach. Our encoder would be some mapping of a node to this highly dimensional embedding vector that we want to reuse, and the decoder is something that takes two vectors, two embedding vectors, and tries to approximate the proximity measure between these vectors corresponding to different nodes. So as here is illustrated, you can see an encoder which takes a node and outputs some high dimensional vector denoted by these letters. And our decoder takes two vectors, for example, some encoded nodes outputted by the encoder. And we want our decoder to take these two vectors and approximate the proximity measure between these two nodes. This is the point of our approach of using encoder and decoder. So the main question is how to train such structure, because we want encoder and decoder to be trained to suit the graph that we're considering. So that is why we'll need some training procedure for this algorithm. And as usually in machine learning, we can take some loss function that suits us and minimize it with respect to the parameters of encoder and decoder. So this is what happens here. For example, we can consider quadratic loss function as in simple linear regression. Then we'll take different nodes that are stored in the graph, Vi and Vj, and try to force our decoder to approximate this the proximity measure between these two nodes. Well, there is a decoder and encoder in this expression, and we want to minimize our loss function with respect to the parameters of the encoder and the decoder. And this is how this decoder-encoder architecture is trained. So there is a table which describes different encoder-decoder approaches that can be applied. I will not focus on this in detail, but you can see that you can take different configurations of your decoder using these vector embeddings Zi and Zj. You can take different proximity measures, for example, based on the adjacency matrix, which tells you how far are the nodes located in your graph. You can take different loss functions. And so this leads to different methods, which somehow let us to store different information in our resulting vector embeddings. But now I would like to focus on node-to-vec method, and we'll deal with the some probability of moving from node Vi to Vj with respect to our graph. So I'll speak of it in more detail. Okay, let me firstly tell you about the softmax operator. It's a very nice thing that is usually exploited, which is frequently used in neural networks, and this operator lets us to transform different coordinates of one vector to a probability distribution. For example, in this picture, we have 5 arbitrary real numbers, both positive and negative, and they are usually called the logits. And what actually does our softmax operator? It takes the exponents of these logits and then divides each logit by divides each exponent of a logit by the sum of all exponents. And if we apply such operation, we'll get these positive numbers, which give us a 1 in total. So we can treat these 5 numbers as some kind of a probability distribution over these input variables. So this construction is frequently used when you train a neural network to classify some data. Usually softmax is applied before actually you have some logits of different classes. And when you apply softmax, you get the probabilities of these classes. And if you want to predict by your neural network some class of your data, you just simply pick the class with the greatest probability. And this is how it is used. But in our case, so once again, for node-to-vec algorithm, we want to take a proximity measure as a probability of going from node Vi to node Vj in our graph. So for example, we consider node Vi and then start some kind of a random walk around this graph, and we can somehow estimate the probability of coming to a particular node Vj. And this is our proximity measure between these 2 nodes. And what actually we can do, we can train our decoder to approximate this probability of coming to node Vj starting from node Vi. And this is where our softmax operator will be used. We just take the vector embeddings Zi, Zj, which were outputted by the encoder. Then we apply softmax operator to different dot products of Zi and different embedding vectors of all other nodes. And then we'll obtain this kind of a probability of coming from Vi to Vj, which is approximated by our encoder and decoder. And so this is the point where we use the softmax operator, which transforms our logits to probabilities. And so the idea of node-to-vec is rather simple. We take our graph, we sample different paths in this graph. For example, we just start random walk from different nodes, then just record this random walk, for example, as in this example, for 4 steps. Then we obtain these sequences. that help us to define the probability of transitions between different nodes, and then we train our encoder and decoder to approximate this probability of random walks. And in the resulting vector embeddings, we'll have some structural information that is related to the probability of transition in our graph. And so let us discuss different advantages and disadvantages of this method. So, as I said, we encode some structural information about the graph with respect to different random walk statistics. And I would say that this method is relatively easy to train, as we have an encoder and decoder, and our encoder just basically some vectors that correspond to different nodes. And so we don't have much parameters here, so this is relatively easy to train. And the disadvantages are that we don't share different parameters between nodes, and this may lead us to overfitting, as we train a separate vector for each node in our graph, so no shared parameters. We also don't use different metadata that might be stored in the nodes of our graph, and this might be useful if we want to get a good quality of predicting. And we also cannot generate embeddings for new nodes, as the procedure is fixed, and we just, after the training procedure, we get the embeddings for all nodes that are already in our graph, and we cannot process the embeddings for new coming nodes, and this is the greatest disadvantage. So we cannot apply simply this algorithm to different nodes. We can consider a different structure of encoding. Actually, we can take our target node Vi and get a large vector of different proximity measures from Vi to all other nodes in this graph. And this will get a high dimensional neighborhood vector, and its dimensionality is equal to the number of nodes in this graph. And then we can use this after encoder and decoder structure to have a bottleneck, and this bottleneck will be actually our vector embedding for this particular node. And so in this case, as it was for encoder-decoder approaches, we have an encoder which takes the high dimensional neighborhood vector and outputs our low dimensional embedding vector. And then, so this is the difference between the current method and the previous one. Our decoder tries not to approximate the proximity measure between two nodes, but rather it takes the vector embedding of our node and tries to approximate the high dimensional neighborhood vector. So we have this kind of a bottleneck architecture. And so once again, we can train our after encoder to minimize the square error between this neighborhood vector and the reconstructed neighborhood vector that is outputted by our decoder. And so this is how this after encoder is trained. And in the end, at the middle of our after encoder, at this bottleneck position, we'll get our vector embedding that can be reused for different tasks. So the main advantage of this method is we share different parameters between different nodes. As here in this picture, we have some kind of a function which maps our neighborhood vector to the embedding vector, and this function is the same for all nodes. So it is parameterized, but by some weights, the same as linear regression, but we usually stack more layers there using some non-linearities. But the main thing there that we share the parameters between different nodes, and this helps us to reduce overfitting. And the disadvantages are that we still don't use any node metadata, which might be stored and which might be helpful for us. And we still cannot generate embeddings for the new nodes, as the dimensionality of this vector is fixed and is equal to the number of nodes in our graph. So if we add new nodes to our graph, everything breaks, as we have a different dimensionality of this vector. So the final algorithm I want to discuss is neighborhood aggregation, which will solve these problems which occurred in neighborhood autoencoders. The main thing here, the main idea is that we want to take our target node and aggregate different features from the neighborhood of this node. And so, for example, here in this picture, we have the neighbors of B being A and C, and we aggregate the vector of features throughout the neighborhood, and we continue the same procedure for all nodes in the graph. And so if we iteratively repeat this algorithm, we will have a resulting vector embedding aggregated all over the neighborhood of different nodes, which actually helps us to use this graph structure of the graph to create like these embeddings that know something about the information stored in the neighborhood nodes. So what happens? Imagine we have some arbitrary graph with different node features written on each node. So for example, here I have two-dimensional vectors, and we would like to build a representation for this central white node. So what we do, we start with taking different vectors that are stored in the neighborhood of this particular node and aggregate them somehow. So in the most simplest case, we just take an average of this vector, but actually you can take any aggregation function you want and to use it to generate this neighborhood vector. So after we finish this procedure, we have the feature vector, which is stored in the node at first, and then we add some neighborhood vector, which is an aggregation of feature vectors around the neighborhood of our node. And so we get these two black and purple vectors. What we do at the next step, we combine these two vectors. So in the most simple case, we just concatenate them, but actually you can consider any combination function that you want. But again, if we consider the most simple case, we just concatenate these two vectors and get a resulting combined vector, which is stored at this node. So there's some activity in chat. I think I'll answer them later. So let us continue speaking about neighborhood aggregation. So at the next step, we take our combined vector, this blue, and apply some linear transformation as is done in linear regression case. So this can be, in other words, we just take some matrix and multiply this vector by this matrix. This is actually our linear transformation. Then we apply some non-linearity as usually done in neural networks. And then we get a new feature vector, which is obtained via this non-linear transformation using the combined vector, which was stored at our node at the previous step. So let us again repeat this pipeline. We have initial feature vectors stored at each node, and we have some feature vectors that are stored at the neighborhood of our node. What we do at the first step, we aggregate these feature vectors using some arbitrary aggregation function. After this procedure, we get our neighborhood vector. Then we combine this neighborhood vector with the initial feature vector stored at this node, and we get a combined vector. Then we apply linear transformation and non-linearity, and we get our new feature vector. This is how it works. And actually, we can apply the same procedure to all nodes in our graph, considering different neighborhoods for each node. And this is somehow we take, if we recalculate these new feature vectors for each node, we'll get these feature vectors updated. And so we can, we repeated this procedure for each node of the graph, but we can repeated several times. For example, we can take different weight matrices that are applied at the as a linear transformation and just repeat these for several times. And this manipulation actually lets us to consider more wide neighborhoods of each node. For example, if we apply this procedure twice, we get the information for this wide node aggregated from this cyan nodes, but as well, when we make the second iteration, we the information from these blue nodes also comes to our white node. So there is also some activity in the chat. What are the values represented in this graph? These might be just some arbitrary data which is stored in your graph. For example, some metadata about the nodes. So this might be anything. If you don't have any metadata, you just can construct it heuristically. For example, take the degrees of each node. But usually when you have your data, apart from the graph itself, usually have some metadata which describes your nodes. So this is the case where you can use it and aggregate it from the neighborhood of each node. And so this is, again, this algorithm I described to you, but written as a pseudocode. So we apply this procedure several times, and we have this hyperparameter k, which is the depth of our neighborhood. So if we apply k times, we consider the neighborhood of width k. So we, for each node of the graph, we aggregate some features from the neighborhood. Then we combine them with the feature vector, which is written in our node. Then we apply some nonlinear transformation using the linear operator and nonlinearity function. There is also some normalization step, but I'll omit it. So this is not so important. And if we apply this procedure recursively k times, not recursively, but consequently, we get the new feature vectors. And so the main thing of this algorithm is that these weight matrices WK, they are trained. So you can consider this structure as a kind of a neural network and optimize these weight matrices using gradient descent. So the structure of constructing these vector embeddings is rather complicated, as it involves aggregation and combination throughout the neighborhood. But actually, you can all operations that we apply here, they are differentiable. There is no problem to calculate the gradients and optimize these structure using gradient descent. And so this is what will be done. And so this will let us to get our vector embeddings. And so discussing the advantages of this approach, we have, again, as in neighborhood autoencoder, we have shared parameters between different nodes. Actually, these are weight matrices that are optimized throughout the gradient descent. We also use metadata stored in the nodes, and our embeddings are aware of this metadata. And so now it is possible to handle new nodes because we can simply take this pipeline once again. And as we have these weight matrices trained, we'll be able to apply this algorithm to the new nodes. So there is no problem. There is no dependence on the number of nodes in the neighborhood or so on. We just simply take our new nodes and apply this procedure with the trained weights of these transformations. So I think this is the most the best one algorithm which takes into account everything that we would like to store in our vector embeddings. So I think this is the most complicated thing we talked today. So the last thing I want to discuss with you is how to generate graph embeddings, because through my talk, I only discuss different cases when we want to generate the embeddings for the nodes. So the most probably simple way you can obtain your graph embedding is just to aggregate these the embeddings of the node. For example, taking the average or actually any aggregation function you want. We also can represent a graph of some kind of a sequence of nodes. For example, you can take your graph and launch something like depth first search or breadth first search, and then you'll get a sequence of nodes, and you can just think of a graph embedding as a sequence of these nodes, and then take an algorithm, for example, recurrent neural networks that are able of processing the different sequence of vectors. There are also more complicated techniques, and they usually use different graph neural networks. So I will not cover this topic at my lecture, but if you're interested in this, you can study some literature that I'll also give you with the slides. So let us summarize the topics we covered with respect to graph machine learning. So we showed that many examples of real-world data, they can be represented as a graph. And so it is usually difficult to process non-trivial data, but what we can do, we can just take some feature extraction algorithms, and then with these high-dimensional vector embeddings, we can take them and process with our favorite classical machine learning methods. And so we discussed also three algorithms for generating graph embeddings, node embeddings. These are node-to-vec. We generate the embeddings trying to preserve the information about random walks in our graph. We considered neighborhood autoencoder when we try to compress different neighborhood vectors of our nodes. And the neighborhood aggregation is a kind of a iterating algorithm which allows us to combine and aggregate the features from the neighborhood of each node. So I think this is it with the theoretical part. So I also here left some links to the papers I studied to prepare this talk for you. So if you are interested in this processing of graphs and building representations for them, you can simply read these papers, and probably you'll find something more interesting in this topic. So there is a question from the chat. How do we compare different node embeddings? Is the reproducibility of the original graph the main metric? Well, actually, it depends on what we want to do with our embeddings. If we want to just store our graph in a compressed way, then we can measure some properties of these embeddings with respect to reconstructing the total graph. But more frequently, we would like to use our embeddings to solve some machine learning tasks. For example, node classification, as we'll do in the practical part. And so I think that it is better to measure the quality of your task, as it is always called a downstream tasks, as we just take our vector embeddings and try to solve some kind of a problem using them. And so the best way to understand if your embeddings are good or not, just take downstream tasks. And how skip-gram is generating embedding node-to-vec? Well, if you're familiar with the node-to-vec, with the word-to-vec algorithm, this is actually the same. What we do, we just if we have something that solves word-to-vec algorithm for us, we just can take different paths of random walks in our graph and interpret them as sequences, as how do they call them? As sentences in each node is a kind of a word, and these paths are like sentences of these nodes. And then we use these. Actually, we have a vector embedding for each node of the graph, and we optimize the I think cross entropy once again. Yeah, cross entropy loss of our softmax and the actual probability of random walk. So this is more complicated in the sense of optimization, and I don't want to focus on it. But the main thing here is that you take your probability of random walk, and using node2vec, you can approximate this probability with the dot products of your embeddings. And actually, it occurs that this information is rather useful if you want to solve a downstream task. So probably I can handle one more question, and then we'll go to the practical part, trying to solve node classification task. Is there a way to know which node to use as a feature vector and neighborhood vector? Well, I'm not sure that you understood me correctly, but actually here every node that is present in our graph is used. Here we have a feature vector of this node, and we aggregate this neighborhood vector throughout the neighborhood. So every node of our graph, it takes a role of being the center of this neighborhood when we aggregate the vectors of its neighbors. And also it plays a role as a neighbor for all nodes that are neighbors to this node. For example, for this cyan node, this white node acts as a neighbor. So if we generate an aggregated vector of neighbors for this cyan node, we take this feature vector of this white node, as well as the feature vectors of these blue nodes. So finally, we'll get the aggregation for this cyan node. So actually, every node acts as a center of neighborhood and as a neighbor for aggregation. So I think I answered the question. If not, just correct me and probably tell something more to direct me to the answer you wish to hear. So if there are no more questions, I would like to move to a practical part. A couple of minutes to set up everything. I think I can share the link to Collab notebook, so you could do it with me if you wish. So I posted it in the Zoom chat, and probably Sergey would repeat this one to a Telegram chat as well. So let us start the practical part. So we'll actually work with the node2vec algorithm and the neighborhood autoencoder. The neighborhood aggregation is slightly more complicated to implement. So I think there are limitations around the internet, so you probably can surf for some websites and GitHubs and find it, but I'll not focus on it today. So let me start my notebook session. And first of all, we install the node2vec package, as it is not included to Collab by default. Yeah. And so we will start with the two example. Actually, Moscow Metro is the most common graph for me, as I deal with it almost every day. And I'm sorry for the foreigners who are not familiar with the map of Moscow Metro, but I think we'll only have the graph properties of our metro map. We actually have different stations as nodes and connections between them as edges, so nothing complicated. And what we will do, we actually can construct a map of our underground using the graph embeddings that we'll build. So actually there is plenty of hard code. I used to set this metro map as a graph using library network X I imported here. So this is a common Python library to store different graphs. And so This one is actually used by the Node2Vec package, and that is why I'm using it here to store the graph. So there are different edges of our metro graph. And now we launch the training of Node2Vec. And so we'll see what happens if we try to. So actually here I created 8D vectors for my stations in this graph. And to illustrate it, I need to convert them to 2 dimensions. And I'll use this algorithm of TSNE, which is usually used for visualizing your embeddings. And so we convert these 8-dimensional embeddings to 2-dimensional using TSNE, and then plot it as 2-dimensional objects. So, yeah, here we have a kind of a sketch of our metro graph. So those who are familiar with the Moscow underground, they might say that, well, actually, for example, here in this real map, we can see 3 stations, the intersection of purple, green, and gray lines. These are Pushkinskaya, Chekhovskaya, and Tverskaya. And here, I think, here at this map, we also have these 3 stations brought together. So actually, we were able to construct a map of our underground using these vector embeddings. So, which is, this is rather simple as it is a 2 example, but this is, I think, interesting in some sense. So, as I mentioned, the embeddings of Node2Vec, they allow us to measure the probability of transition between different nodes and between different stations in our case. So we can take Tverskaya station, which is a green station here, and we can get our embeddings from the Node2Vec and measure the probability of transition to different other nodes, taking the softmax of dot products with the embeddings of other stations. So let me take this one. And so we have transition probability to Mayakovskaya equal to roughly 0.14. We have to Belaruskaya green about 0.1, and to Tverskaya itself, so a kind of a loop to the same station, it is 0.08. And we can see actually that here is our Tverskaya station. So here is Mayakovskaya, which is rather close to it. And this is our green Belaruskaya station. So there are the biggest probabilities of transition correspond to the nodes which are close at our graph. Something wrong with the sound? Please answer anyone. That's okay. So let us continue. Yeah. Okay, let us move to real data. Actually, in this notebook, I'm using the Cora dataset. It consists of 2,700 scientific publications. These are different machine learning papers, and these publications are divided into 7 classes. So our task would be to predict these classes for the nodes of our graph. And actually, as these publications form a graph, as it is common to cite, if you publish your machine learning paper, you have to cite the previous papers that you are using in your work. So that is why we have a graph of citations here, which includes about 500.5 links. So we have 2,500 publications and 5,000.5 links between them. And we also have some metadata in this graph. Well, these are just some, I think, code words that can be found in different papers. And so for each publication, we also have two 1,400 different features that correspond to this metadata. So we download our graph from the source, and then we start preprocessing. Actually, what we do here, we take our label encoder to move these names of the classes to just numbers from 0 to 6, and then we load our data. So this is how our metadata looks like. Here we have plenty of features. We also had our target class. So these different topics of our publications. And here we have different IDs of the publications, which help us to identify these publications. And we also have a different pandas table, which tells us about different stations between these publications. So actually, this is a kind of a list of edges of our graph, I believe. So we have, for example, I think paper number 35 cites paper number 1033, and so this is how we have more than 5,000 of edges in our graph. So firstly, we get our X with features and our Y with classes. And then we split them into training tests, as usual is done in machine learning. So to measure how successful are our graph methods, we need a baseline to compare. And for the baseline, I decided to take this simple logistic regression built on top of the initial features, this metadata of publications. So let me import it from sklearn and just train simple logistic regression with cross-validation on our regularization parameter. So I think those who are familiar with the sklearn library, there is nothing for them in this cell. So the train finished, and we can print our results. So here we have 75% test accuracy and almost 100% train accuracy, which means that we have like sufficient overfitting. So this happens because we have like very many features. So they have the same order of magnitude with the number of samples, which is not good. So usually these types of data, they lead to overfitting. That is why I want to use dimensionality reduction for this data, and this is what is done with PCA. And I heard that Anastasia, like she told something about the PCA in the first lecture, so I think you're a bit familiar with it. So we use PCA from sklearn again and transform our train and test data using the PCA compression. And so once again, we take our logistic regression and try to fit it on our PCA compressed data. So even faster, as you see, we reduced the number of features from 1,400 to 256. So that is much less, and then we will have faster fitting. And so we can see that we underwent the drop of accuracy by 1%, even 1.5%. But actually, we reduced overfitting. So here we don't have 97%, but rather just 90%. And so this is probably not better than the initial baseline, but we'll later concatenate these PCA compressed features with our graph features, just to use both graph information and the information stored in the nodes to obtain a better model. So we'll just leave these PCA features for now and just focus on our graph embeddings. So what we try at first is our node2vec. So we simply imported it from the appropriate library and just use it from scratch. So nothing complicated. So what happened here? First of all, the transition probabilities were estimated. So I actually didn't mention it in my lecture, but there are hyperparameters of node2vec, which allow you to tell if you want more like deeper walks or more wider walks around your graph. And so if you like vary these hyperparameters, you get different transition probabilities. But so this is more for tuning your hyperparameters, and so I think this can be done using, I don't know, grid search or Bayesian optimization. Nevertheless, I don't want to focus on it now, so we just take the hyperparameters by default. So now we're waiting for our node2vec to be fitted. So around a half of a minute remaining. You can also ask your questions in the chat. And we'll have to wait for a while for different algorithms to be fitted. So I'll spend this time on answering your questions. So almost there. Now we generated. Is it because together? So I think this is not a question for me, but rather for the algorithmizers. So actually, for this progress bar, we generated different random walks, and now the algorithms. It actually fits a word2vec model that is hidden inside this node2vec, and then our embeddings will be generated. So I think we'll have to wait a little more until everything finishes. This is rather boring, I would say, but we have to deal with it as we are doing machine learning here, and so different algorithms. They take time to be fitted. So these are not these complicated neural networks, but anyway, that's it. So we have these embeddings generated, and they have the dimensionality of 128. So we'll now try to take our embeddings, which were generated for train and test, and simply fit a logistic regression on top of these features. So this will take some more time. Any way of tuning the parameters of node2vec? Well, actually, there are plenty of hyperparameters. For example, the dimensionality of these output embeddings and these different random walks hyperparameters I mentioned. And so I think the best way to tune them is just simply use cross-validation or with grid search, as it is usually done if you tune many hyperparameters. So I think there is no specific way to tune them for node2vec, just all instruments you usually use to fit your hyperparameters. So we have our logistic regression fitted. Now try to measure accuracy. So you see, so our baseline was around 75%, and now using only graph embeddings, we obtained around 82, well, 81 to 82%, so which is rather great, I think. Is it good to bit model generator for this node2vec? I don't understand actually what do you mean. Could you please provide more details on your question, please, and then probably I'll answer. So now we can try to combine our graph features with the initial node features, just to concatenate these PCA compressed data and our embeddings, and train a new model on top of these combined features. Yep, finished. And now we measure our accuracy. So pretty good, I would say. We increased accuracy by 20%, which is rather great. I'll make a model pipeline like you merge with the logistic regression with node2vec. I think you can. Well, actually, Scala provides some instruments for you to combine this into a single pipeline. I'm actually not using it frequently. I don't like this interface. Just I prefer to fit every algorithm individually, but I don't see any problems if you wish to combine these node-to-vec, just include it into your Scala pipeline. So I think it will work if you properly. I think there might be a problem with the interface, but I think you can just probably write some Python class on top of your node-to-vec, and there will be no problem to including it into Scala pipeline. So this is it with the node-to-vec. So this is, I think, this is a good increment of our accuracy. Sorry, you seem to be using some test nodes information during the graph embeddings. Did I understand it correctly? Well, actually, no. When building these graph embeddings, we simply only use the information about the graph. So this is the citations network. So for building embeddings, we use only graph information. There is also information stored in the nodes, but we only add it here when we tune our logistic regression. So you may say that, well, this is not great because you just you take the information about your testing nodes, but this is okay because here we use what is called unsupervised learning, because we get our embeddings without using any information about the labels. So in this sense, our test nodes, they're absolutely the same as train nodes. So no problem about overfitting and something like that. And you're absolutely right that we're using here the test nodes. Yeah, but this is not a problem. And so the last thing I want to cover here is the neighborhood autoencoder. So here, as a proximity measure, I use the negative exponent of the negative distance between the nodes in the graph. So the distance is like the common distance you use in the graphs, just the number of nodes separating, the number of edges separating these two nodes. And so this proximity measure has some nice properties. For example, if we take the proximity of the node with itself, we get exactly 1, because so I'm sorry, I have to correct it. This is wrong. If we take the proximity measure of the node with respect to itself, we get exactly 1 because the distance between the node and itself is 0. So we take an exponent of 0 and get 1. And so if two nodes are not connected in our graph, we have the distance infinity. And in this case, we get the proximity measure of 0, which is also rather like natural to have. And so this proximity measure is also bounded. It is from 0 to 1. And I also want to mention that it is important that here we use the undirected version of our graph, because otherwise, well, actually we can think of a citation network as a directed graph, because like there is a difference between you cite someone and someone cites you. So this is not the same. And but if we use an undirected version of the graph here, the graph and the matrix of distances, it would be too sparse and we'll not be able to like build any algorithms on it. So this is why I use an undirected version of the citations network. And this allows us to obtain nice features. So here I'm using PyTorch library for constructing a neural network and training it. So I think you'll have the part about the neural networks tomorrow, but so I'm apologizing for this, but I think no problem. Yes, I'm using TQDM as well, as it creates nice progress bars. So let us start. Here I built this graph once again. Yeah, and now I'm generating calculating different distances between my nodes in the graph. So now I have to create a distance matrix between different nodes of my graph using these distances which were computed by the network X library. And then I just take my distance and apply an exponent to it. I also have a hyperparameter tau here, which actually is, well, if you know what is softmax temperature, this is exactly it. But for one-dimensional case, this is just needed to like renormalize my distance for my in order for my exponents not to be too small, because if the distance between these nodes is like, for example, 15, which is like, it's okay for the graph, we'll have an exponent of minus 15, which is about a 0. So this would be like similar to the case when we have the nodes disconnected from the graph. And so that is why I use some normalization hyperparameter in order for these proximities to be not too small for me. So now so this is what TQDM library does. It creates a progress bar for me, and I can see how much time it is until the finish of my processing. So once again, here I'm creating this proximity measure matrix between different nodes. And later I will use my neighborhood autoencoder in order to compress the vectors of this matrix, which actually are neighborhood vectors of my nodes. So as we're waiting, I'll tell something about my autoencoder. This is simply a multi-layer perceptron model, so nothing complicated here. I think you'll hear, if you're not familiar with the neural networks, you'll hear about them tomorrow. Here I'm just using 3 layers to reduce the dimensionality of my feature vectors and, well, my neighborhood vectors to say. So I'm defining this PyTorch model, which actually stores my encoder and decoder for the autoencoder architecture. So now I define some necessary stuff which is required for training in PyTorch, and then I'll start this training loop for 10 epochs of training. And in some moments we'll see the graph of the loss function. So as a loss function, we simply use the mean squared error loss, which is like common for training vanilla autoencoders. So actually, if you're familiar with the concept of autoencoders, the neighborhood autoencoder is simply it, like no modifications, but you use your neighborhood vectors as the like feature description, like the features of your nodes. So this is simply a way how to apply this autoencoder to the graph data. So the method itself is rather simple. So here we have the graph of loss. So we decayed until the 10th epoch. And now we have the autoencoder trained, and we can take the embeddings which are stored at the bottleneck layer of the autoencoder. So here we have the dimensionality of 512. And now we take our encoder embeddings and feed the logistic regression on top of it. So a little bit more time to wait until fitting. Probably some more questions if you have them. So it took around a minute for us to wait for the fitting. This is because I suppose these dimensions are rather large, and we have the they're actually dense and not sparse, and that is why it takes time to process and fit our logistic regression models. So yeah, here we see as well our result is much better than the initial logistic regression. It's about 82%. So probably we can concatenate it with our PCA compressed metadata of nodes to obtain a better result. So we do this as well. And this actually would be our last task for today. And so we got around 83–84%, which is not better of the combination of node2vec and the PCA features, but anyway, it is still better than the logistic regression, and it is much better. So by 8%, I would say. So I think this is it for today from the talk about the graphs. And so I want to summarize a little bit for you. So the main point I want you to understand after my lecture is that, well, at first it may seem that processing graphs is rather difficult because they don't have some data structure that we are familiar with. But anyway, using some math and our classical machine learning algorithms, we can use feature extraction and representation learning for these graphs. And then if we obtain our features and embeddings, we can make we can build like very strong baselines, which are much better than the regular baselines like logistic regression, just applying simple methods like node2vec. Actually, there are more complicated methods about the graphs, for example, graph neural networks, and I didn't cover this today. But anyway, I want you to understand that there is no need to be afraid of such tasks, which are about non-trivial examples of data. And so I think this is the main point I wanted for you to understand. And so I'm very pleased that there are a lot of good listeners and for your questions today. And so I hope you also learned something new today throughout these 3 lectures. So thank you. And I leave this scene for Sergey.
Thanks a lot, Ildus, for a wonderful talk. And it seems that people are really involved and interested in the topic. So now we're having another break before our very last session. It will be short, but it will give you the basis for next 24 hours where you will be involved in the competition, in the contest, I mean, in training contest. So see you in like 22 minutes, basically. 4:45, we are meeting here again. Okay.
Hello, everyone. My name is Alexey Birshert, and I'm a lecturer and an intern researcher at the High School of Economics, Moscow, Russia. Today, I will tell you about the mini machine learning contest that we will give you from 5 p.m. today to 5 p.m. tomorrow, Moscow time. Thus, you will have 24 hours to participate and solve it. Now, let's take a look at how it would happen. The contest is held on a website called kaggle.com. It is the most popular website for hosting machine learning competitions. You can participate in competitions to gain experience, can discuss different machine learning and data science related topics in the discussion sections, explore datasets and notebooks with model training and visualization pipelines. Now, let's take a closer look at our competition. Let's talk a little bit about the task. In today's world of developing stress and anxiety, more and more people suffer from sleep disorders. It's quite obvious that insomnia strongly affects people's lifestyles, and along with that causes economical and even social safety problems. Moreover, it may lead to other yet unexplored long-term consequences. In our competition, you will need to solve the binary classification problem. You are offered to solve a task of predicting insomnia given a person's physical, health, and lifestyle parameters. On the competition landing page, as you can see, you would have a data tab where you can check what data we've provided you with. You would have 3 files: train.csv, the training set, test.csv, the test set, and a sample submission.csv, a sample submission in the correct format. In the data, you would have several features, several columns. Let's take a closer look. Firstly, you have an ID column that serves as a person's ID. Next, we have age in years, height and weight, a height in centimeters and weight in kilograms. Yeah. Sex corresponds to a person's sex. Next, we have stress, level of stress during last month, categorical values from 1 to 3. The higher the value, the higher the stress. Doctor, relative number of visits to doctor previously, also categorical values from 1 to 3. The higher the value, the higher the number of visits. Sport, a binary column, whether the person is physically active or not. Pernicious, 1 and 2. 2 binary columns, whether the person has bad habits, alcohol and smoking. UBP and LBP, upper and lower blood pressure in millimeters of mercury, and insomnia. The target column, binary target, whether the person has sleep disorders or not. Note that this column only appears to be in the train set, but not in the test set. The overall goal of the competition is to predict the insomnia column for the given test set. As for the evaluation, I have logistic loss, so the less, the better. When you first get to the Kaggle website, you should register there to participate. Afterwards, you should accept the competition rules. Generally, you have 3 ways to participate in the competition. You can train your models and analyze the data in Google Colab, at Kaggle, and locally. We will provide you with 2 baseline notebooks, one to work in Google Colab and one to work at Kaggle. Let's take a closer look at the notebooks. Both notebooks are identical, except the part where we download the data from Kaggle and where we make a submission. If your choice is to work with Google Colab, then first you need to open your account page on the Kaggle website and to click the Create New API Token button, yeah, and to open the generated file. Next, you need to paste your username and token in the cell below, yeah, and run it. After that, after you run this cell, all the cells with exclamation mark Kaggle commands will work just fine. So here you can see the command for downloading the data from the Kaggle website for the competition. Remember to accept the rules of the competition before participating in it. A command for submitting a sample submission, yeah, for making test submission, and a command for submitting a final solution, a final submission. You can check the baseline's code and exploratory data analysis later on by yourself. We will share the Google Colab link with you after my presentation. Otherwise, if you choose to work with on Kaggle, we don't have to worry about any API tokens or keys. You just need to click copy and edit notebook button, yeah. And after you obtain your very own baseline notebook copy, you can run it and submit output files to the competition. Here you can see a corresponding button. In our competition, we have two leaderboards, public leaderboard and private leaderboard. The first one, public leaderboard, it contains around 1/3 of the test set data, and it is available through the whole competition. The private leaderboard contains the rest 2/3 of the test set and would become available to the competitors after the competition ends, so at 5 p.m. tomorrow. We will ask a couple of people from the top on the private leaderboard to prepare a short presentation of their solution for about 5 minutes and present it tomorrow at 6:30 p.m. Moscow time. The speakers will be awarded merch. You will have 20 attempts today till midnight UTC and 20 attempts tomorrow. We are opening the competition at 5 p.m. Moscow time today. Good luck and have fun. All the links for the baseline notebooks and for the competition will be sent to you via email and Telegram chat. Thank you for your attention. We think that you should participate. You can participate in comments, but you don't need a comment to participate. You can do it alone, or you can join some other participants to work in a comment. Yeah. You can make 20 submissions today till midnight UTC and 20 submissions tomorrow. Once again, I repeat, you can participate on your own base, and you can choose team. You can communicate in the Telegram chat and participate as a team. Score will be based on the log loss, logistic loss. The metric calculation is provided in the baseline notebook, so you can check it yourself. So, any more questions? Okay, thank you very much. Thank you for your attention. The prize, there will be only prizes for top. Actually, I think the question about the prizes is for Sergey.
Yeah, thanks a lot, Alexey. Yeah, we just decided randomly to give you some souvenirs to the best solutions. So that's it. Some souvenirs. Like branded with HEC or IDAO. So that's it. Just to make you slightly more motivated to submit all 40 attempts. So if you don't have any questions either to me or to Alexey, as you told, in a bit we'll send the links to chat and via email. So check it in a couple of minutes and you'll have access to the task. Okay, I guess we wrap up the Zoom session for today and basically move to chatting on Telegram and emails. So thanks a lot for being with us. For almost 5 hours, and I hope that you learned a lot. And so let's try to use this knowledge on practice now. Okay, see you online today and on Zoom tomorrow.